Hello there and welcome to Physics with William, where curiosity gets comfortable, everyday things become unexpectedly strange, and science is allowed to take its time. Tonight we're going to look at something so familiar that you've probably seen it several times today without giving it much thought. Water. It fills glasses, runs from taps, falls from clouds, freezes into cubes, boils in kettles, and generally behaves so predictably that we rarely expect it to surprise us. We know the basic rules, or at least we think we do. Cool water enough and it becomes ice. Heat it enough and it becomes vapor. Freezing belongs at one end of the temperature scale, boiling belongs at the other, and there should be a comfortable distance between them. Except there is a particular set of conditions in which water refuses to follow that simple picture. It can begin to boil while it is also beginning to freeze. Bubbles can appear in liquid that is becoming colder, and ice can form while some of the water is escaping as vapor. Nothing is broken, nothing supernatural is happening, and the water has not become confused. It is simply responding to two things that determine its state: temperature and pressure is the part of the story that we usually forget. Before we get into exactly how that can happen, I would love to know where you are listening from tonight and what the weather is like outside your window. Perhaps you are somewhere warm enough that ice feels like a distant concern, or perhaps you are listening under a blanket while the temperature outside makes freezing water seem entirely reasonable. Maybe there is a glass beside you, a cup of tea, or one of those bottles of water that somehow spends the entire day following you from room to room without actually being finished. Wherever you are, it is worth remembering that the water around you is living under a very specific set of physical conditions. We are so accustomed to those conditions that we mistake them for the only way water can behave. Change the surroundings, especially the pressure, and the rules that feel obvious in an ordinary kitchen can become surprisingly flexible. If you find this kind of gentle scientific wandering relaxing, you can give the video a like and subscribe to the channel. It helps this quiet corner of physics reach more curious people, and it gives us an excellent excuse to keep investigating substances that appear innocent until someone puts them inside laboratory equipment. Most people first encounter boiling as a temperature. You put water into a kettle, switch it on, wait for the familiar noise, and eventually bubbles begin racing upward. The water has become hot enough to boil. That experience is so common that boiling and high temperature become almost inseparable in our minds. If something is boiling, we assume it must be very hot. In ordinary life, that is usually a safe assumption. Touching a boiling saucepan merely to test the philosophy of phase transitions is not recommended. But scientifically, boiling is not defined by a particular temperature. Boiling is a process in which vapor bubbles can form throughout a liquid and continue growing instead of being crushed by the pressure around them. The temperature needed for that to happen depends on the pressure surrounding the liquid. Lower the pressure, and the temperature required for boiling falls with it. Reduce the pressure enough, and water that would normally feel only mildly warm can begin to boil. Reduce it further, and water can boil while becoming cold. The atmosphere plays a much larger role in your kettle than it appears to. Air has mass, and gravity pulls that air toward Earth. The enormous amount of atmosphere above us therefore creates pressure at the surface. We do not normally notice it because we have lived with it every moment of our lives, and our bodies are well adapted to it. Yet that pressure is constantly acting on objects around us, including the surface of water. When a tiny pocket of water vapor tries to form inside a liquid, the surrounding pressure pushes inward against it. If the vapor cannot push back strongly enough, the bubble collapses. Heat the water, however, and its molecules move more vigorously. More molecules enter the vapor state, the vapor pressure increases, and eventually bubbles can survive and expand. That is when boiling becomes visible. The important point is that the water is not simply reaching some universal temperature where it receives permission to boil. It is reaching a condition where the vapor inside the bubbles can compete successfully with the pressure around the liquid. You can see evidence of this without needing a particularly exotic experiment. Travel to a high mountain and the atmospheric pressure becomes lower because there is less air above you. Water there boils at a lower temperature than it does near sea level. The difference can matter while cooking because food sitting in boiling water may actually be cooking at lower temperature. The saucepan can bubble enthusiastically and still take longer to prepare dinner. The bubbles are telling you that the water is boiling. They are not giving you a reliable report of exactly how hot it is. This is one of those occasions where dinner accidentally becomes a physics demonstration, although anyone waiting for potatoes to soften at high altitude may not appreciate the educational opportunity. Now, imagine taking the same idea much further than climbing a mountain. Instead of carrying water upward through the atmosphere, place it inside a strong chamber from which air can be removed. A vacuum pump begins drawing gas out of the chamber. As more air disappears, the pressure above the water decreases. Nothing has to heat the water. The container can begin at ordinary room temperature. At first, the surface may appear almost unchanged. Then, as the pressure continues falling, bubbling begins. Water that was nowhere near the temperature we normally associate with a kettle starts boiling. If you had only the image and not the surrounding information, you might assume someone had secretly placed a heater beneath it. But the reason is the opposite of what our everyday instincts suggest. The water has not been given extra heat. The external pressure has been taken away. This already feels unusual, but the next step is what turns the demonstration into something memorable. When water changes from liquid into vapor, the escaping molecules carry energy with them. Becoming a gas requires molecules to separate from neighbours that attract them. The molecules that escape are generally among those with enough energy to break away, and when they leave, the average energy remaining in the liquid decreases. The liquid cools. This is the same broad reason evaporation makes your skin feel colder. Step out of a swimming pool, and even on a reasonably warm day you may suddenly feel chilled. Water evaporating from your skin takes energy away with it. Sweating uses the same process deliberately. Your body places moisture on the skin, evaporation removes heat, and you cool down. It is an elegant system right up until you're wearing a shirt that reveals exactly how hard it is working. Inside the low-pressure chamber, the boiling water is doing something similar, only much more rapidly. Molecules are escaping into vapor, carrying energy away from the liquid that remains. Because the chamber is kept at low pressure, evaporation and boiling can continue strongly. The water loses energy and its temperature drops. It may have started near room temperature, but it becomes colder as more of it changes into vapor. If enough energy is removed, the remaining liquid eventually reaches conditions where ice can form. At that moment, you can have water visibly bubbling while portions of it are freezing. One part of the sample is changing from liquid to gas, while another part is changing from liquid to solid. The boiling contributes to the cooling that makes freezing possible, so the two processes are not merely happening beside one another by coincidence. One helps create the conditions for the other. That is the central trick, although calling it a trick makes physics sound slightly more mischievous than it really is. Water boils because the pressure has become extremely low. The boiling causes rapid energy loss. The energy loss lowers the temperature. The falling temperature allows ice to form. Once those ideas are placed in the correct order, boiling and freezing at the same time stop being contradictory. What seemed impossible came from an assumption that boiling always means very hot. Remove that assumption, and the behaviour becomes understandable. The water does not need to be hot in the ordinary sense to boil when the external pressure is low enough. There is another reason this feels difficult to accept at first. We tend to imagine a container of water as though the entire substance must choose a single state. It is either liquid, frozen, or boiling away as vapour. Real matter is less tidy. A glass containing ice and water already contains two states at once. A covered container of water normally has some water vapour above the liquid even if you cannot see it. Molecules constantly move between these states. Water molecules leave the liquid surface and become vapour. Other vapour molecules collide with the surface and return to the liquid. At an ice surface, molecules can leave the solid arrangement while others join it. The boundaries are active even when the overall object looks completely still. If you could watch individual molecules rather than the visible water, There would be no single instant when every molecule agreed to do the same thing. Some would have more energy than others. Some would be moving faster. Some would be interacting with neighbouring molecules in slightly different ways. Temperature describes the behaviour of enormous numbers of particles rather than giving every molecule an identical amount of motion. This is important because phase changes emerge from the collective behaviour of those particles. When conditions favour vapour, more molecules can escape. When conditions favour solid ice, more molecules settle into an ordered structure. Under carefully chosen conditions, multiple processes can occur together. We usually learn the states of water with 3 clean examples. Ice is solid. Water in a glass is liquid. Steam or water vapour is gas. Those categories are useful, but nature does not place thick walls between them. An ice cube placed in a drink can be melting while water elsewhere on its surface freezes for brief microscopic moments. A puddle can evaporate long before it is anywhere close to boiling. Frost can form directly from water vapour. Ice can slowly disappear into dry air without first becoming a visible puddle. The transitions between states are always determined by the surrounding conditions and by how energy moves through the system. Pressure becomes especially important because gases take up much more space than liquids. When a water molecule escapes from liquid and joins the vapour, it becomes part of a phase in which molecules are widely separated. If the environment pushes strongly against that expansion, becoming vapour is harder. If the environment provides very little opposing pressure, the vapour phase becomes much easier to enter. This is why removing air from the chamber has such a dramatic effect. The liquid suddenly finds itself in surroundings where molecules can escape much more readily. The boiling point falls until boiling is possible at the water's current temperature. The water then begins paying the energy cost of that escape. Each molecule entering the vapour phase requires energy, and much of that energy is drawn from the water itself. Without a heater continually replacing the lost energy, the remaining liquid gets colder. This is sometimes missed when people first watch the experiment, because the visual language of boiling is so closely connected to heating. Bubbles seem like evidence that energy must be entering the water. Here they are part of the reason energy is leaving it. Suppose you are able to place your hand inside the chamber, which you should not do for several practical reasons, and somehow touch the water safely as the process continued. The bubbling liquid would not feel like the contents of a freshly boiled kettle. It would be cooling. Continue lowering the pressure, and eventually you would be looking at a mixture that may contain liquid water, water vapour and ice. The scene appears to violate common sense only because common sense was trained at ordinary atmospheric pressure. Our everyday intuition about water is therefore extremely local. It is based on life near the surface of Earth. We have spent years observing water under pressures that vary, but usually not enough to overturn our basic expectations. Weather systems change atmospheric pressure. Elevation changes it more noticeably. Yet neither usually takes us into the very low pressure environment where cool water can boil violently. Laboratory equipment can move beyond that familiar range and reveal behaviour that was present in the laws of physics all along. There is a useful comparison with people who live at different elevations. Someone cooking near sea level develops one expectation for how boiling water behaves. Someone living high in the mountains becomes accustomed to another. Neither person has changed the nature of water. Their environments simply provide different pressures. A vacuum chamber extends that difference far beyond normal living conditions. Once the pressure becomes sufficiently low, the relationship between liquid and vapour changes dramatically. Freezing introduces its own balance. Liquid water molecules are mobile and constantly changing neighbours. In ice, they settle into a more organised structure. Removing energy from liquid water reduces molecular motion and allows that solid structure to become stable. During the vacuum experiment, the energy removed by rapid vaporization can cool the liquid enough for that arrangement to begin forming. Ice may appear around parts of the remaining liquid while bubbling continues nearby. The exact appearance depends on the equipment, the amount of water, how quickly pressure is reduced, and how heat moves between the water and its container, but the underlying reason remains the same. There is something satisfying about watching the process because it exposes a mistake hidden inside an ordinary word. We often use hot and boiling almost as though they mean the same thing. They do not. Hot describes temperature in a relative everyday sense. Boiling describes a phase transition. Under the conditions we normally experience, those ideas happen to arrive together, so our brains merge them. Physics separates them again. The same distinction matters in the opposite direction. Freezing does not simply mean that a substance has reached one immutable temperature regardless of circumstances. Pressure can affect the boundary between liquid and solid as well. Water is especially interesting because ice has an unusual structure. Its solid form is less dense than liquid water, which is why ice floats. That familiar fact has consequences for how water responds to pressure near the freezing boundary. We will return to that later, because water has managed to make even the apparently simple act of becoming ice slightly more complicated than many substances do. For the moment, the important idea is that the state of water cannot be predicted from temperature alone. You need to know pressure as well. Give me only a temperature and ask whether water must be liquid, solid, or gas, and the information may be incomplete. The surroundings matter. A temperature that produces ordinary liquid water at one pressure can produce boiling at another. Conditions that allow ice in one situation may favour a different state somewhere else. Scientists organise these possibilities by mapping where different states are stable. Imagine changing temperature in one direction and pressure in another, then marking what water does under each combination. Large regions belong mainly to solid ice, liquid water, or water vapour. Between those regions are boundaries where two states can coexist. Along one boundary, solid and liquid can both be present. Along another, liquid and vapour can coexist. Elsewhere, solid water and vapour can share the conditions. Then comes the particularly interesting place where those boundaries meet. There is one precise combination of pressure and temperature at which solid water, liquid water, and water vapour can all coexist in equilibrium. Ice can be present, liquid can be present, vapour can be present. Molecules can move between all three states while the overall conditions remain balanced. This is known as the triple point of water, and it is the deeper idea waiting behind the dramatic demonstration of water boiling while it freezes. The phrase equilibrium can make the situation sound motionless, but microscopic equilibrium is anything but still. Molecules continue changing state. Some leave the liquid and enter the vapour, others return. Some join the ice, others leave the ice. What remains stable is the overall balance between those processes. Imagine a busy railway station where equal numbers of people enter and leave each minute. From far away, the crowd size appears unchanged, even though individuals are constantly moving. Water near its triple point behaves in a comparable way at the molecular level. This helps explain why the boiling and freezing demonstration is more than a clever laboratory curiosity. It gives us a direct view into the way phases of matter depend on conditions. We see that states are not absolute labels attached permanently to certain temperatures. They are outcomes of a competition involving molecular motion, intermolecular attraction, pressure, and energy. The molecules themselves do not know whether we call the sample ice, liquid water, or vapour. They simply respond to the forces and energy around them. When they have enough freedom and energy to separate widely, the gas phase becomes possible. When they remain close but mobile, we see a liquid. When conditions favour a stable, ordered arrangement, ice forms, change the surroundings and the balance changes with them. This becomes especially clear when you consider the strange sequence happening inside the vacuum chamber. The experiment may begin with perfectly ordinary liquid water. Air is removed, pressure falls, the boiling threshold falls with it. The water starts boiling without additional heating. Vapour carries energy away. The remaining liquid cools. Ice begins forming. Boiling can continue while freezing occurs. Eventually, depending on the setup, much of the liquid may disappear or freeze, and the behaviour changes again as the available energy and material are redistributed. Every stage follows ordinary physical rules. The surprise comes from seeing familiar rules operating outside familiar conditions. That difference between familiar conditions and universal laws appears throughout physics. A heavy object and a light object behave one way when dropped through air, yet remove the air, and their motion reveals something deeper about gravity. A clock seems to tick at the same rate everywhere until speed and gravity become extreme enough for relativity to matter. Water seems to require great heat to boil until pressure is reduced. Our intuition is usually built from the narrow part of nature we experience directly. Experiments allow us to push beyond it. Water is particularly good at creating these moments because we know it so well. If an obscure chemical boiled at an unexpectedly low temperature in a vacuum, most of us would simply accept that obscure chemicals are entitled to strange hobbies. But water feels personal. We drink it, cook with it, wash in it, watch it freeze, and listen to it boil. We feel qualified to predict what it should do. That confidence makes its unusual behavior much more effective at exposing the limits of intuition. There is also a practical reason scientists care about the relationship between pressure and phase changes. Processes involving vacuum and evaporation are used in laboratories, manufacturing, food preservation, cooling systems, and technologies designed to remove moisture from materials. Freeze-drying, for example, takes advantage of phase behavior under low pressure to remove water from frozen material in a way that would be difficult under ordinary conditions. The details go beyond our opening question, but the basic lesson is already familiar. Change pressure, and water gains routes between states that ordinary kitchen experience does not prepare us for. Even our atmosphere provides gentler versions of the same physics. Clouds, frost, snow, evaporation, condensation, and ice formation all involve water moving between states as temperature and pressure vary through the environment. The spectacular vacuum chamber demonstration is not using different laws. It is simply arranging those laws in a particularly clear way. So when you see water bubbling while ice appears, there is no need to decide whether the water is really boiling or really freezing. Both descriptions can be correct. Some molecules are leaving the liquid and becoming vapor. Other molecules are becoming part of the solid structure. The system can support more than one transition because the pressure is low enough for vaporization and the temperature has fallen enough for freezing. The idea becomes even more interesting when we stop asking only how water can perform these two changes and ask where the exact boundary between all its familiar states lies. There is a particular condition where ice, liquid, and vapor do not merely appear during a rapidly changing experiment, but can exist together in a carefully balanced state. That meeting place is where our ordinary categories of frozen, liquid, and boiling water come together, and understanding it means looking at the strange point where three different versions of the same substance can all be present without any one of them immediately taking over. To understand that meeting place, it helps to forget for a moment the neat picture most of us carry around in our heads, where ice belongs in one box, liquid water belongs in another, and vapor belongs somewhere above the kettle. Those categories are useful in ordinary life, but they make the boundaries between states seem much sharper than they really are. Nature is perfectly comfortable allowing different states of the same substance to exist together. A glass with ice floating in it already gives us solid water and liquid water sharing the same space. A closed bottle that contains liquid water also contains a small amount of water vapor above the surface. Even an ordinary ice cube sitting in a freezer may exchange molecules with the air around it. What seems unusual is not that water can occupy more than one state at once. What is unusual is finding the precise conditions where solid, liquid, and vapor can all remain present together without one quickly eliminating the others. Picture a sealed container with a small amount of ice at the bottom, some liquid water around it, and water vapor filling the space above. From the outside, the scene might look almost disappointingly calm. There is no explosion, no dramatic cloud of steam, and no ice cube attempting to escape the container. Yet on the molecular scale, there is constant activity. Molecules are leaving the liquid surface and entering the vapor. Other vapor molecules are colliding with the liquid and becoming part of it again. At the surface of the ice, some molecules are joining the solid structure while others leave it. The water is not sitting still at all. It is simply changing in several directions at rates that can balance one another. That balance is important because coexistence does not mean nothing is happening. It means opposing changes are happening at matching rates. Think about a busy railway station in which people are constantly arriving and leaving. If 100 people enter during a certain period and 100 people leave, the number of people in the station stays the same. From a distance, you might say the crowd is stable, but stability does not mean inactivity. Matter behaves in much the same way when different phases coexist in equilibrium. Molecules keep moving, but the overall proportions can remain steady. The word equilibrium sometimes sounds as though everything should be perfectly still, which is understandable because in everyday speech we often use balance to mean something has stopped moving. In physics, equilibrium can be much busier. A glass of water sealed inside a container can reach a condition where molecules evaporate from the surface, while other molecules condense from the vapor at the same average rate. The amount of liquid remains nearly constant, but individual molecules are continually changing state. If we could label one molecule and follow it, it might leave the liquid, spend some time in the vapor, return to the surface, and later escape again. The substance looks stable only because enormous numbers of molecules are performing these transitions in a balanced way. Now bring ice into that picture. At the boundary between ice and liquid water, molecules can move in both directions as well. Some leave the organized structure of the solid and become part of the liquid. Others from the liquid settle into positions within the ice. If melting happens faster than freezing, the ice shrinks. If freezing happens faster than melting, the ice grows. If the rates balance, the boundary can remain roughly where it is, even though molecules continue crossing it. This gives us two familiar examples of coexistence. Ice and liquid water can share a boundary, and liquid water and vapor can share another. There are also conditions where ice and water vapor can interact directly without liquid water being the main intermediate state. You may have noticed this if ice cubes left in a freezer for a long time gradually become smaller or develop rough surfaces. Some water molecules can leave the solid and enter the vapor directly. The reverse process happens when water vapor turns directly into ice, as it can when frost forms on a sufficiently cold surface. Water has several possible routes between its familiar states, and which route dominates depends on the surrounding temperature and pressure. This is where the idea of a meeting point begins to make sense. If there are conditions where solid and liquid can coexist, conditions where liquid and vapor can coexist, and conditions where solid and vapor can coexist, then it is reasonable to wonder whether there is a special set of conditions where all three relationships can be balanced at once. There is, but before giving that condition too much attention, it is worth understanding why such a point should exist at all. Imagine changing the temperature of water very slowly, while keeping the surrounding pressure controlled. At one set of conditions, ice is the stable state. Add enough energy and liquid becomes favoured. Continue changing the conditions and vapor eventually becomes favoured. Now imagine repeating the experiment at a different pressure. The temperatures at which those transitions occur can shift. Water does not carry a fixed instruction saying it must freeze or boil at exactly the same temperature, regardless of the environment. The surrounding pressure changes the competition between the phases. If you could record all those observations and arrange them into a kind of map, you would find regions where solid water is stable, regions where liquid water is stable, and regions where vapor is stable. The edges of those regions are especially interesting because an edge represents conditions where two phases can coexist. Cross one boundary, and ice begins turning into liquid, or liquid begins turning into ice. Cross another, and liquid becomes vapor, or vapor condenses into liquid. Somewhere else, ice and vapor exchange directly. The boundaries are not just lines drawn by scientists because diagrams look nicer with lines. They represent real physical balances. On one side of a boundary, one phase is more stable. On the other side, another phase is more stable. Right on the boundary, neither has completely won. Both can exist together. Now imagine following those boundaries until they approach one another. There comes a place where the distinction between three separate two-phase balances disappears. Solid can coexist with liquid. Liquid can coexist with vapor. Solid can coexist with vapor. All three conditions meet. That is the strange meeting point we're interested in. What makes it so unusual is not simply seeing ice, water, and vapor in the same container. You can create that casually. Put an ice cube into warm water on a humid day, and there will be solid ice, liquid water, and some water vapor in the surrounding air. But that is not the special balance we're describing. In the ordinary glass, those states are not all in equilibrium with one another. The ice is probably melting, water is probably evaporating, the surrounding air may be carrying vapor away, the proportions are changing. At the special meeting condition, the three states can coexist in a much more exact balance. There is no need for the ice to disappear immediately, no need for all the liquid to boil away, and no need for all the vapor to condense. Molecules continue moving between states, but the overall system can remain stable as long as the temperature and pressure are held at the required values. This distinction between simply being present and being in equilibrium is worth keeping in mind because it appears everywhere in science. A room can contain ice, water, and vapor without representing anything unusual. The remarkable part is creating conditions where the three phases are simultaneously stable against one another. Water makes this especially interesting because its solid form behaves in an unusual way. For most familiar substances, the solid is denser than the liquid. Pack the particles into an organized solid structure, and they generally take up less space. Water does something different. When it freezes into ordinary ice, its molecules arrange themselves into a structure that occupies more volume than the same amount of liquid water. That is why ice floats. This simple fact has enormous consequences. Lakes freeze from the top rather than the bottom. Ice can form an insulating layer over liquid water beneath it. Aquatic ecosystems can survive winters that would otherwise be far more destructive. Your drink keeps its ice cubes near the surface instead of hiding them at the bottom like small frozen stones. It also means that pressure affects the solid and liquid forms of water in a somewhat unusual way. We do not need to go deeply into that yet, but it is useful to notice that water is not a perfectly ordinary substance. Its molecular structure gives it behaviors that differ from many other materials. The same hydrogen bonding that helps make water such a good solvent and gives it a relatively high boiling temperature also shapes the structure of ice and influences how its phases meet. At the molecular level, liquid water is already a complicated place. Molecules are constantly forming and breaking temporary attractions with their neighbours. They do not move independently like tiny marbles bouncing around a box. They tug on one another, rotate, rearrange, and repeatedly build brief networks of interaction. In ice, those relationships become much more organised. The molecules settle into a repeating structure with more persistent positioning. In vapour, they are far more separated and spend much less time interacting. Changing phase therefore means more than changing how fast molecules move. It also means changing how they are arranged and how strongly their interactions shape the overall structure. Temperature influences the energy available for motion. Pressure influences how favourable compact or expanded states are. The state we observe emerges from the balance between these effects. This is why a single sample can sometimes support multiple states at once. Near a phase boundary, the energetic advantage of one state over another becomes very small. A molecule at the surface of ice may find conditions nearly equally suitable for remaining in the solid or joining the liquid. A molecule at the surface of liquid may find vapour accessible. Under the right conditions, none of the three familiar phases has an overwhelming advantage. It is tempting to imagine this as a kind of three-way contest where ice, water, and vapour are struggling to take control of the container. That is not quite how molecules experience it, but the picture is useful. Away from the meeting point, one side usually has an advantage. Raise the temperature, and the solid becomes less favoured. Lower the pressure and vapour becomes easier to form. Change both carefully, and the balance can move until all three phases are equally allowed. There is also something important happening with energy whenever molecules cross these boundaries. Melting ice requires energy. Freezing releases energy. Turning liquid into vapour requires energy. Condensing vapour releases energy. Moving directly between solid and vapour also involves an exchange of energy. These transfers help determine whether a phase transition continues or settles into equilibrium. Suppose some liquid begins to evaporate in a sealed system. The vapour builds up above the liquid. As more vapour molecules accumulate, more of them collide with the liquid surface and condense. Eventually, the rate of condensation can match the rate of evaporation. At that point, liquid and vapour coexist in dynamic equilibrium. Something similar can happen between ice and liquid water. If the conditions are right, melting and freezing balance. Add vapour to the picture, and another set of exchanges becomes possible. The extraordinary meeting point occurs when all these relationships fit together under one precise combination of conditions. A useful way to understand why the balance is delicate is to imagine disturbing it only slightly. Raise the temperature a little while, keeping other conditions similar, and the solid phase becomes less stable. Ice begins to disappear. Lower the temperature slightly and freezing becomes more favourable. Change the pressure and the relative stability of vapour shifts. The meeting point is therefore not a broad region where anything goes. It is a very specific crossing. That specificity is one reason the phenomenon became scientifically useful. When nature provides a reproducible condition that depends on fundamental properties of a substance rather than on an arbitrary object, scientists become interested. A carefully prepared sample of pure water can reach the same characteristic coexistence condition again and again when the pressure and temperature are controlled properly. That consistency makes the point more than a curiosity. It becomes a reference. For a long time, measuring temperature accurately was more difficult than simply deciding that a liquid felt hot or cold. Thermometers had to be calibrated. Different instruments had to agree. Scientists needed reliable reference conditions that laboratories in different places could reproduce. Phase transitions offered useful anchors because substances change state under well-defined circumstances when pressure and purity are controlled. Water was especially valuable because it is common, well-studied, and capable of producing a particularly precise three-phase balance. The details of how this became connected with temperature standards have changed over the history of measurement, but the physical condition itself remains an important reference in thermometry. What is appealing about the meeting point is that it takes something very ordinary and reveals how carefully nature organises it. We usually see water in whatever state our environment favours. A lake is liquid because the temperature and pressure support liquid water. Snow is solid because colder conditions favour ice. A cloud contains tiny droplets or ice particles because atmospheric conditions permit them. None of those forms is permanent. Alter the surroundings and the same molecules reorganise. At the meeting point, the usual hierarchy disappears. Ice is not simply waiting to melt. Liquid is not simply waiting to boil. Vapour is not simply waiting to condense. All three can participate in a balanced exchange. The scale of the molecules involved makes this even stranger to think about. A visible droplet contains an enormous number of water molecules. Each molecule is unimaginably small compared with the container, yet the collective behaviour of all those molecules produces a sharp, reproducible, macroscopic condition. There is no central coordinator telling the molecules when to freeze or evaporate. The balance emerges automatically from their interactions and the surrounding conditions. This is one of the recurring themes in thermodynamics. Large-scale order often emerges from huge numbers of tiny events. Temperature itself is a collective property. Pressure is a collective property. Phase behaviour is collective. A single molecule cannot meaningfully be called a glass of liquid water. It takes vast numbers of molecules interacting for the familiar properties of liquid water to emerge. That helps explain why phase changes can appear sudden, even though molecular activity is continuous. Warm an ice cube and molecules at its surface begin gaining enough freedom to leave the solid arrangement. As more energy enters, melting becomes obvious. Heat liquid water under the right pressure and vapor formation increases until bubbles can grow throughout the liquid. The visible transition looks abrupt because the collective behavior changes once certain conditions are reached. Near the meeting point, several such collective possibilities overlap. This system sits at the intersection of states that would normally dominate in different regions. A slight disturbance chooses a direction. Imagine increasing the pressure while maintaining conditions otherwise close to the meeting point. Vapor becomes less favourable because the gas occupies much more volume than the condense phases. Molecules are encouraged back toward liquid or solid forms. Reduce pressure instead and vapor becomes easier to sustain. Adjust temperature upward and molecular motion favours less ordered states. Move downward and the solid becomes more competitive. These shifts are why a diagram of water states can be so informative even without mathematics. It is essentially a map of which form of water wins under different environmental conditions. The meeting point is the crossroads. The idea also changes how we think about boiling. Earlier we saw that water can boil at low temperature if the pressure is sufficiently low. Follow that reasoning toward even lower pressures, and you eventually approach conditions where liquid water has only a narrow range in which it can remain stable. Below a certain pressure, ordinary liquid water cannot simply sit there as the stable middle state between ice and vapor. The behavior becomes dominated by direct transitions involving solid and gas. That fact matters in places very different from a laboratory. On worlds with extremely thin atmospheres, liquid water can be difficult to maintain at the surface. Even if temperatures occasionally seem suitable, pressure may be too low for stable liquid water to persist for long. Water can freeze, evaporate, or move directly between ice and vapor, depending on the local conditions. This is one reason planetary scientists care about pressure when discussing whether liquid water can exist on another planet. Temperature alone does not tell the whole story. Mars is an obvious example because its atmosphere is much thinner than Earth's. Conditions vary across the planet, and the behavior of water there depends strongly on local temperature and pressure. Ice can exist, vapor can exist, and brief liquid conditions may become possible in special circumstances, but the broad point is that low pressure changes the rules dramatically. A temperature that would allow a comfortable puddle on Earth does not guarantee a comfortable puddle elsewhere. Even on Earth, the atmosphere creates a range of environments where pressure changes enough to influence water's phase behavior. Mountain climbers encounter lower boiling temperatures. Weather systems move pressure up and down slightly. Deep underwater environments add pressure rather than remove it. Industrial systems deliberately manipulate pressure to control boiling, condensation, drying, and cooling. The meeting point therefore sits inside a much larger story about how matter responds to its environment. It is not a strange exception where water suddenly behaves differently from normal. It is a landmark within the same set of relationships governing every kettle, freezer, cloud, glacier, pressure cooker, and vacuum chamber. What makes the laboratory version special is that we can isolate those relationships. Instead of weather, altitude, sunlight, wind, impurities, and countless other variables all changing at once, scientists can control the temperature and pressure carefully. The behavior becomes easier to study. Purity matters too. Ordinary tap water contains dissolved minerals and gases. Seawater contains salts. Even distilled water can acquire dissolved gases from the air. These extra substances can shift freezing and boiling behavior. Anyone who has spread salt on an icy pavement has used this principle without needing to think about molecular thermodynamics. Salt changes the conditions under which liquid water and ice coexist, helping ice melt at temperatures where pure water would behave differently. For precise experiments, scientists therefore care about exactly what kind of water they're using. the cleaner and better characterized the sample, the more precisely its phase behavior can be reproduced. This is another reminder that simple phrases such as water, freezes at a certain temperature, are usually summaries that assume a particular pressure and composition. The meeting of ice, liquid, and vapor also reveals why our everyday definitions can become slippery. If you point at a container holding all three and ask what state the water is in, there is no single answer. Some is solid, some is liquid, some is gas. The substance as a whole occupies several phases. That is not a failure of classification. It is exactly what the classification system predicts. The same thing happens with many other substances. Water is not unique in having a condition where three phases can coexist. Other pure substances have their own corresponding meeting points at different temperatures and pressures. What makes water especially familiar is that its phases are part of everyday life. We regularly encounter its solid, liquid, and gaseous forms without needing specialized equipment. Water also has more solid forms than the ordinary ice in your freezer. Under different pressures, water molecules can arrange themselves into several distinct crystalline structures. Most of those forms require conditions far removed from everyday life. Under very high pressures, entirely different kinds of ice become stable. This means the full map of water is far more complicated than simply ice, liquid, and vapor. For our purposes, however, the familiar ice found at normal pressures is enough to reveal the basic idea. One substance can have different stable arrangements, and the surroundings determine which arrangement is favored. If you think back to the boiling and freezing experiment, you can now see why the sight of bubbles and ice in the same container is only the beginning. The experiment is guiding the water toward a region where the distinction between liquid, solid, and vapor becomes unusually delicate. As pressure is removed, boiling cools the liquid. As temperature falls, ice forms. The system moves through conditions where multiple phases can be present, but the exact meeting point is more controlled than the dramatic demonstration. In a rapidly pumped vacuum chamber, the pressure and temperature may be changing continuously, so the system can sweep through different phase conditions. The boiling and freezing are visible because the water is moving from one situation toward another. A true equilibrium point asks for something more precise. The temperature must be held at the required value. The pressure must also be held at the required value. The water must be sufficiently pure. When those conditions are met, all three familiar phases can coexist in stable balance. There is almost something reassuring about how exact this is. The experiment may look bizarre, but underneath it lies an orderly physical relationship. Nature is not improvising. The same conditions produce the same behavior. This is why physicists and chemists are so fond of phase diagrams and carefully controlled experiments. What looks confusing in the visible world often becomes clear when the correct variables are identified. If you only watch the water, boiling and freezing together appears contradictory. Add pressure to your understanding and the contradiction disappears. Add the idea of phase equilibrium and the behavior becomes part of a larger pattern. The next step is to look directly at that precise crossing point because it has a name, a very particular temperature, a very particular pressure, and a surprisingly important place in the history of measurement. It is called the triple point of water, and once we examine what those conditions actually mean, the strange meeting of ice, liquid, and vapor becomes even more exact than the boiling and freezing demonstration first suggests. The triple point of water is the name given to that precise condition where ice, liquid water, and water vapor can all exist together in equilibrium. And the word precise matters here because this is not a broad range of temperatures where water simply becomes indecisive. It is a very particular combination of temperature and pressure. For pure water, the temperature is just above the ordinary freezing point, at 0.01 degrees Celsius, while the pressure is extremely low compared with the atmosphere around us, a little more than 611 pascals. That pressure is only a tiny fraction of normal atmospheric pressure at sea level. If you are somehow expecting the triple point to involve violent heat, glowing equipment, or a laboratory full of warning lights, It is rather less dramatic than that. The temperature is barely above freezing. The strange part is the pressure. Remove almost all of the surrounding air, control the conditions carefully, and water reaches a place where its three familiar forms can stand together in balance. This is different from simply having ice, liquid, and vapor in the same room. Your kitchen may contain ice in the freezer, water in the sink, and water vapor in the air, but nobody would call the kitchen a triple-point apparatus, which is probably good news for whoever designed the kitchen. Even a glass containing ice and liquid water with some vapor above it is not automatically at the triple point. The important requirement is equilibrium. At the triple point, the three phases are not merely present. They are all stable under the same temperature and pressure. Molecules can pass from one phase to another in every direction, and the overall balance can remain steady. Imagine looking closely at the boundary between a small piece of ice and the liquid water touching it. Molecules at that boundary do not know that one side has been given the label solid and the other side has been given the label liquid. They respond to the energy and forces around them. Some molecules leave the organized structure of the ice and join the moving liquid. Other molecules from the liquid settle into positions in the solid. If more molecules leave the ice than join it, the ice melts. If more join than leave, the ice grows. At equilibrium, these processes balance on average. The visible boundary can stay in roughly the same place while microscopic movement continues constantly. Now look at the surface between liquid water and vapor. Molecules leave the liquid and escape into the gas. Other molecules from the vapor collide with the liquid surface and become part of it again. If evaporation dominates, the liquid shrinks. If condensation dominates, the amount of liquid increases. At equilibrium, the average rates balance. The same idea applies between ice and vapor. Molecules can leave the solid directly and enter the vapor, and vapor molecules can settle directly onto the ice. When all three-phase relationships are balanced at the same time, the system has reached the triple point. There is a useful way to think about how unusual this is. Under most conditions, one phase has a clear advantage. Put an ice cube on a warm plate and liquid water becomes the more stable form, so the ice melts. Place liquid water in a sufficiently cold freezer and the solid phase becomes favoured, so ice grows. Leave a puddle in dry air and some molecules escape into vapour. Heat water strongly under ordinary pressure and vapour formation becomes vigorous enough for boiling. In each case, the surroundings push the system in a particular direction. At the triple point, the competition becomes almost perfectly balanced. Solid, liquid, and vapour can all remain present because the conditions do not strongly favour the complete disappearance of any one of them. This balance is delicate because changing either temperature or pressure moves the water away from that special condition. Raise the temperature slightly while keeping the pressure near the triple point, and ice becomes less stable. Lower the temperature and the solid gains an advantage. Increase the pressure and the vapour becomes less favourable, because the surrounding pressure works against the widely separated gas phase. Reduce the pressure and liquid water becomes increasingly difficult to maintain. The triple point is therefore not a comfortable neighbourhood with plenty of room to wander. It is more like a very specific address, and water only behaves this way while you're standing at that address. The reason pressure has such a strong effect becomes clearer when we compare the phases themselves. Water vapour occupies vastly more volume than the same amount of liquid water. Its molecules are widely separated, moving through the available space with much less contact than molecules in a liquid. When external pressure is high, expanding into that gas state requires pushing against the surroundings. When external pressure is very low, that resistance becomes much smaller, so vapour is easier to form. This is why reducing pressure allows water to boil at lower temperatures, and it is also why the triple point occurs at a pressure far below ordinary atmospheric pressure. At normal sea level pressure, the atmosphere pushes too strongly for the triple point arrangement to exist. Near the ordinary freezing temperature, ice and liquid water can coexist, but vapour cannot join them in the same equilibrium in the required way. The surrounding pressure is simply much too high. To reach the triple point, the pressure must be reduced until all three phase boundaries meet. That is why the phenomenon belongs naturally in vacuum equipment rather than on a kitchen counter. There is an important difference here between the ordinary freezing point of water and the triple point temperature. We often say that water freezes at 0 degrees Celsius. That is a useful everyday statement under approximately normal atmospheric pressure. The triple point, however, occurs at 0.01 degrees Celsius under its much lower characteristic pressure. The difference in temperature is tiny, only 1/100th of a degree, but the physical situation is very different. At ordinary atmospheric pressure, you're considering the balance mainly between ice and liquid water. At the triple point pressure, ice, liquid, and vapor can all participate in the equilibrium. That tiny temperature difference also helps explain why the triple point became important in the history of temperature measurement. Scientists need reference conditions that can be reproduced accurately. Saying that something should be measured at a cold room temperature is not especially useful because different rooms have different opinions about cold. A physical condition defined by the behavior of pure matter is much better. For many years, the triple point of water played a central role in defining and calibrating temperature scales, because a carefully prepared sample could reproduce the same physical state with remarkable consistency. Historically, the temperature of the triple point of water was assigned a particular value in the thermodynamic temperature scale, and that relationship helped define the Kelvin. Modern measurement standards have changed. The Kelvin is now defined using a fundamental physical constant rather than being tied directly to one particular sample of water. Even so, triple point cells remain useful in high-precision thermometry because the physical transition is so reproducible when the water and experimental conditions are carefully controlled. A triple point cell is a specially constructed container designed to produce this equilibrium accurately. It contains very pure water in a sealed environment, and the geometry allows ice, liquid water, and vapor to coexist under controlled conditions. Scientists can place a thermometer into a central well and compare its reading against the known behavior of the water. The device may look rather modest compared with the importance of what it does. There are no dramatic flames, no giant magnets, and no need for someone in a white coat to shout that the experiment has become unstable. Instead, the value comes from quiet reproducibility. Prepare the cell correctly and nature provides the same reference condition again. Purity matters because dissolved substances change phase behavior. Ordinary tap water is not just water molecules. It contains minerals, dissolved gases, and other substances in small amounts. Those additions can change the temperature at which freezing occurs and alter the balance between phases. Seawater demonstrates this very clearly because its dissolved salts lower the freezing temperature compared with pure water. The same principle is used when salt is spread on icy roads. The salt mixes with liquid water at the ice surface and changes the conditions under which freezing and melting balance. For a precise triple point measurement, scientists therefore need water of carefully controlled composition. There is also a historical detail that reveals just how serious precision becomes at this level. Water from different natural sources can contain slightly different proportions of hydrogen and oxygen isotopes. These variations are extremely small, but when measurements become precise enough, even those differences can matter. High-precision standards therefore specify the composition of the water used for reference measurements rather than assuming every sample collected from every river, cloud, glacier or kitchen tap is physically identical in every measurable respect. This is a good example of how science changes when you move from everyday accuracy to laboratory accuracy. In daily life, water is water. In precision metrology, someone eventually asks exactly which water you mean. The triple point is also useful because it reveals something fundamental about phase diagrams. Imagine again the invisible map of temperature and pressure that describes where different phases of water are stable. One region belongs to ordinary ice, another belongs to liquid water, another belongs to vapor. The borders between them represent conditions where two phases can coexist. The line between solid and liquid contains combinations where melting and freezing can balance. The line between liquid and vapor contains combinations where evaporation and condensation can balance. The line between solid and vapor represents conditions where water can move directly between ice and gas. All three lines meet at the triple point. That meeting explains why liquid water has a lower pressure limit for stable existence. Below the pressure associated with the triple point, there is no ordinary route where you can warm stable ice and simply obtain a stable pool of liquid water before reaching vapor. Instead, solid water can move directly toward the gas phase through sublimation. This does not mean that a liquid molecule can never appear for an instant under unusual non-equilibrium circumstances. It means that stable bulk liquid water does not occupy that region of the phase map. Dry ice provides a familiar comparison, although it is made of carbon dioxide rather than water. Under ordinary atmospheric pressure, solid carbon dioxide does not melt into a puddle. It changes directly into gas because normal atmospheric pressure lies below the pressure needed for liquid carbon dioxide to be stable at those temperatures. Water behaves differently at ordinary pressure because our atmospheric conditions allow a large liquid region. But take water below its triple point pressure, and a somewhat similar idea appears. Ice and vapor can become the relevant stable phases without ordinary liquid water occupying the middle. This is one reason pressure matters so much when scientists discuss water on planets and moons. If a world has surface temperatures that occasionally rise above the freezing point, that does not automatically mean lakes and puddles can exist there. The atmospheric pressure also has to permit a stable liquid phase. A thin atmosphere can make liquid water unstable, even at temperatures that might sound comfortable by Earth standards. Water may begin to evaporate rapidly, cool itself, freeze, or move between ice and vapor depending on the exact environment. Back in the laboratory, the triple point gives us a cleaner version of the same principle. A sample of water is placed under carefully controlled pressure and temperature, and the three phases are allowed to coexist. If the system is disturbed, it responds by shifting material between the phases. Add a small amount of heat, and some ice may melt or liquid may turn into vapor. Remove heat, and more solid can form. Change the pressure and the vapor balance shifts. Phase changes act as a kind of buffer, because energy can go into rearranging the state of matter, rather than simply changing temperature immediately. This connection between phase change and energy is important. When ice melts, energy is required to break down the more organized solid structure and allow molecules to move as a liquid. When liquid water becomes vapor, even more energy is needed to separate molecules widely into the gas phase. The reverse transitions release energy. At the triple point, all of these possible exchanges exist within the same system. The balance depends not only on how much energy the molecules have, but also on how pressure influences the relative stability of each phase. Water adds one unusual complication, because ordinary ice is less dense than liquid water. For many substances, applying pressure favours the solid because the solid takes up less volume. Water's common form of ice occupies more volume than the liquid, which changes how the melting boundary responds to pressure. Increase pressure near the ordinary melting condition, and liquid water can become slightly more favourable because it occupies less volume than the ice. This unusual behaviour is tied to the open molecular structure created when water freezes. That structure is also the reason an ice cube floats. Water molecules in ordinary ice arrange themselves in a network that leaves more open space than exists in the liquid. When the ice melts, parts of that open structure collapse and the molecules can pack more closely. It is one of water's most famous peculiarities, and it has enormous consequences for life on Earth. Because ice floats, lakes and ponds can freeze from the top downward, the surface ice then slows further heat loss and helps liquid water remain beneath it. If ordinary ice sank, bodies of water could behave very differently during winter. At the triple point, however, We are not mainly interested in the ecological consequences of floating ice. We're interested in how this unusual solid structure participates in a three-way thermodynamic balance. The solid has its own molecular organisation, the liquid has a more mobile network, and the vapour consists of widely separated molecules. The triple point is the condition where none of these large-scale arrangements has a decisive advantage over the others. It is easy to picture the process incorrectly, as though individual molecules are choosing between three doors. In reality, there are enormous numbers of molecules interacting, colliding, exchanging energy, and responding statistically to their environment. Some happen to be at surfaces where changing phase is possible. Others remain within the bulk material. The stable coexistence emerges from the collective behaviour of all of them. This is why thermodynamics can make very precise predictions without tracking every molecule individually. Trying to follow every water molecule in even a tiny sample would be hopelessly impractical. There are far too many. Instead, scientists describe large-scale properties such as temperature, pressure, volume, and phase. Those collective quantities allow us to predict what the material will do, even though the microscopic motion remains extraordinarily complicated. At the triple point, those large-scale quantities line up in a particularly elegant way. The temperature is fixed by the coexistence condition. The pressure is fixed by the coexistence condition. If all three phases remain present in equilibrium, trying to add a little energy does not simply send the temperature climbing immediately. Some of the material can change phase instead. Likewise, removing energy can shift material toward the solid state. This ability of phase changes to absorb or release energy, while temperature remains nearly stable, is familiar from ordinary melting and boiling, but at the triple point several possible transitions are available at once. Suppose you could watch a perfectly prepared triple point cell for a long time, with an imaginary microscope capable of seeing molecules. You would not see three peaceful populations staying on their own side of neat borders. You would see water molecules continually switching membership. A molecule in the ice might eventually leave its position and enter the liquid. A liquid molecule might escape into vapour. A vapour molecule might land on the ice. Another might return to the liquid. The identity of the molecules in each phase would change even while the visible quantities of ice, liquid, and vapour remained almost constant. That idea of dynamic equilibrium is one of the most important lessons hidden in the triple point. Stability in nature does not always mean stillness. Sometimes stability means that change in one direction is matched by change in another. A crowded city can maintain a roughly constant population while thousands of people arrive and leave. Your bloodstream can maintain concentrations of substances while molecules are continually being used and replaced. An ecosystem can appear stable while individual organisms are born and die. In the same way, a phase equilibrium can look motionless while molecular traffic continues everywhere. The delicacy of the triple point also means it cannot be maintained casually in an open container. If you expose the system to ordinary atmospheric pressure, the pressure immediately moves far away from the required condition. If heat leaks in or out without control, the balance changes. If impurities are introduced, the phase boundaries shift. The experiment therefore depends on careful isolation and preparation. This precision is part of what makes the boiling and freezing demonstration so useful as an introduction. In that demonstration, pressure is reduced and boiling removes energy from the water. The temperature falls until freezing begins. The system may pass near conditions associated with the boundaries between phases, producing the remarkable sight of boiling and freezing together. But a rapidly changing demonstration is not necessarily sitting exactly at the triple point in perfect equilibrium. It is often moving through a sequence of states. The triple point itself is calmer. Once the exact pressure and temperature are established and all three phases are present, the system can remain balanced. The spectacular bubbling may no longer be the main feature. What matters is the coexistence. This difference is useful because dramatic experiments sometimes encourage us to focus on what is visually impressive rather than what is physically important. Bubbles and ice forming together are memorable. The deeper result is that pressure and temperature jointly determine phase stability. The triple point is the cleanest expression of that idea because all three familiar phases meet in one condition. It also reminds us that familiar temperatures such as freezing and boiling points are never completely independent of the environment. When someone says water boils at a certain temperature, there is an unstated pressure condition hiding in the sentence. When someone says water freezes at a certain temperature, pressure and composition are hiding there too. Under ordinary everyday conditions, those assumptions are so consistent that we rarely mention them. Physics becomes more interesting when we remove the assumptions and ask what happens elsewhere. This is why pressure will become increasingly important as we continue. Lowering it can turn room temperature water into vigorously boiling water. Increasing it can raise the temperature required for boiling, which is why pressure cookers can cook food more quickly. Pressure can shift the balance between ice and liquid, affect the way water behaves deep beneath Earth's surface, and determine whether liquid water can remain stable on another world. The triple point is only one tiny location on a much larger map, and once we begin moving away from that location, the rules of boiling and freezing start changing in ways that are both practical and surprisingly easy to observe. Pressure is easy to overlook because most of the time it does its work quietly. We wake up, walk around, make coffee, open windows, boil water, freeze leftovers, and rarely think about the enormous atmosphere pressing on everything around us. The pressure of the air feels so normal that our brains simply remove it from the picture. Yet when water changes between liquid, solid, and vapor, pressure is one of the main things deciding what happens. Temperature matters certainly, but temperature does not make the rules by itself. Change the pressure and familiar landmarks such as boiling and freezing begin to move, sometimes enough to produce behavior that would seem impossible if all you knew was ordinary life at sea level. A kettle gives us a useful place to begin because it hides pressure physics in something completely ordinary. When water is heated, its molecules move more vigorously, and more of them become capable of escaping from the liquid. Long before boiling begins, molecules are already leaving from the surface through evaporation. A forgotten glass of water will slowly lose water even if nobody heats it. Boiling begins when vapor can form not only at the surface, but inside the liquid itself. Small pockets of water vapor appear between the surrounding liquid molecules, and if those pockets can survive, they grow into bubbles and rise. The survival of those bubbles is where pressure enters the story. A vapor bubble is surrounded by liquid, and the surface of that liquid is itself exposed to the pressure of the atmosphere. The outside world is pushing inward. If the vapor inside a newly formed bubble cannot push strongly enough against its surroundings, the bubble collapses before it can grow. Heating the water increases the tendency of molecules to enter the vapor state, and eventually the vapor pressure becomes strong enough for stable bubbles to form throughout the liquid. We then say the water is boiling. Under ordinary conditions near sea level, this happens at the familiar boiling temperature we learn in school. But that temperature is not a permanent property that water carries around regardless of where it goes. It depends on the pressure outside the liquid. Lower the surrounding pressure, and the bubbles have less resistance to overcome. The water can boil while its molecules have less thermal energy, which means boiling occurs at a lower temperature. Anyone who has cooked at high altitude has encountered this effect whether they wanted a physics lesson or not. As you climb higher through the atmosphere, there is less air above you. Atmospheric pressure falls. Because the outside pressure is lower, water begins boiling at a lower temperature. It can bubble just as vigorously as water at sea level, while actually being cooler. This matters for cooking, because the food cares about the temperature of the water rather than the enthusiasm of the bubbles. Beans, potatoes, pasta, and other foods can take longer to cook at high elevations, because boiling water there is not as hot. A mountain is only a modest beginning. If you continue reducing pressure far beyond what you could reach simply by climbing, the boiling temperature continues falling. Put ordinary water inside a vacuum chamber and begin pumping out the air, and eventually the water can start boiling without being heated at all. It may begin near room temperature. The pump lowers the pressure around it until the conditions allow vapor bubbles to grow. Suddenly, the surface becomes active. Bubbles appear, and the water looks as though someone has turned on a hidden stove. Nothing has secretly heated it. The pressure has changed. This is one of the most useful corrections to our everyday understanding of boiling. Boiling does not mean extremely hot. Boiling means that liquid and vapor have reached conditions where vapor bubbles can form throughout the liquid. Under the pressure around us in daily life, reaching those conditions requires considerable heating. Under low pressure, it does not. There is a slightly uncomfortable consequence of this if you imagine environments where atmospheric pressure is extremely low. Exposed liquid water can begin boiling even when it does not feel hot. A person seeing the bubbling might instinctively associate it with heat, but the molecules are responding to pressure instead. Physics has no obligation to match the kitchen associations we built during childhood. Pressure can move the boiling point in the opposite direction as well. Increase the pressure above the water, and vapor bubbles have more resistance to overcome. The liquid must become hotter before boiling can continue. This is the principle behind a pressure cooker. Steam is trapped inside the sealed vessel, causing the pressure to rise. Because the pressure is higher, the water can remain liquid at a temperature above its normal boiling temperature. Food cooks faster because it is surrounded by hotter water and steam than it would be in an open saucepan. So one pressure change makes water boil while cooler, while the opposite pressure change lets liquid water remain unboiled while hotter. The substance has not changed. The environment has. This same principle becomes important inside engines, industrial equipment, cooling systems, power stations, laboratories, and spacecraft. Engineers cannot simply ask how hot a liquid is. They also need to know the pressure. A liquid that behaves normally in one part of a machine may begin producing vapor bubbles somewhere else if the local pressure falls. Those bubbles can sometimes create problems. One example is cavitation, which can happen in pumps, propellers, and flowing liquids. When water moves through a region where the pressure becomes sufficiently low, tiny vapor bubbles may form even though the water has not been heated anywhere near the temperature normally associated with boiling. The bubbles travel into regions of higher pressure and collapse. When many bubbles collapse rapidly near a surface, the effect can be surprisingly damaging. Over time, metal can become pitted and worn. A ship propeller turning through water can create low-pressure regions around its blades. If the pressure drops enough, vapor bubbles appear. A moment later they move or the pressure changes and the bubbles collapse. The water may never have been remotely close to boiling in the kitchen sense, yet locally it has undergone the same kind of liquid to vapor transition. Once again, pressure changes what the word boiling really means. Freezing is affected by pressure too, although here water behaves in a way that makes it somewhat unusual. Most substances become denser when they freeze. Their molecules settle into a solid structure that occupies less space than the liquid. Water does the opposite under ordinary conditions. When water freezes into familiar ice, its molecules arrange themselves into an open structure that takes up more volume than the liquid water did. That is why ice floats. The solid is less dense than the liquid beneath it. It is such a familiar sight that we rarely stop to consider how odd it is. Drop a piece of solid metal into its molten version, and in many cases the solid would sink because it is denser. Ice sits proudly at the surface of water as though this were completely normal behavior. The expansion during freezing also explains why a forgotten bottle of water can crack in a freezer. As ice forms, the water attempts to occupy more space. If the container cannot expand enough, the pressure against its walls can become large. Pipes can be damaged in cold weather for the same reason. Water trapped inside freezes, expands, and pushes against the pipe. Because ordinary ice occupies more volume than liquid water, increasing pressure can favour the liquid state near the normal freezing point. Pressure tends to encourage states that occupy less volume, and in this particular comparison, liquid water is more compact than ordinary ice. As a result, applying pressure can lower the melting temperature of ice slightly. the effect under everyday pressures is small. Pressing an ice cube between your fingers is not going to produce an impressive pool of water through pressure alone. Your hand mostly contributes heat, which is much more important in that situation. But under controlled conditions, the pressure effect can be measured clearly. This unusual relationship has led to a famous explanation for ice skating that often appears in simplified science discussions. The story says that the narrow blade of the skate creates high pressure on the ice, lowering its melting point and producing a thin layer of water that makes the surface slippery. Pressure can indeed influence the melting point, but the full physics of ice skating is more complicated. Friction, heating, and the natural properties of the ice surface also matter. The simple pressure explanation contains a real physical effect, but it is not the entire story. That is a useful warning because pressure effects can be easy to exaggerate. Physics is often taught using one clean mechanism at a time because it helps us understand the ingredients. Real situations may combine several effects. A skate involves pressure, friction, heat, surface structure, and motion. A boiling kettle involves atmospheric pressure, heat transfer, dissolved gases, convection, and the rough surfaces where bubbles begin forming. The underlying principles remain useful, but nature rarely promises to demonstrate them one at a time. When pressure becomes very high, water becomes stranger still. Ordinary ice is only one of several possible solid structures water can form. Under pressures far beyond everyday experience, water molecules can arrange themselves into different forms of ice, some much denser than the ice in a freezer. Scientists give these different structures separate names and classifications because their molecular arrangements are genuinely distinct. Deep inside large icy moons and planets, pressures can become great enough for some of these unusual forms of ice to exist. A substance we associate with snowflakes and cold drinks can form dense, solid phases under conditions no household freezer could approach. This is another reminder that terms such as ice describe a much larger family of physical possibilities than everyday experience suggests. Returning to lower pressures brings us back toward the phenomenon of water boiling and freezing at the same time. Suppose we begin with liquid water in a chamber and steadily remove the air. Pressure falls, so the boiling temperature falls. Eventually, the current temperature of the water becomes high enough relative to the reduced pressure for boiling to begin. Once boiling begins, molecules escape into vapor. Turning liquid into vapor requires energy, and much of that energy comes from the water itself. The remaining liquid cools. As the temperature falls, the conditions move closer to those favouring ice. Continue removing pressure and allowing vapor to escape, and the cooling can become strong enough for freezing to begin. Notice what pressure has accomplished. It did not directly freeze the water in the way a freezer removes heat. Instead, it changed the conditions for boiling. The resulting vaporization removed energy, and that energy loss cooled the water until ice could form. Pressure changed one phase transition, which then helped drive another. This relationship is common in cooling technology. When a liquid evaporates, it can absorb energy from its surroundings. Refrigeration and air conditioning systems exploit phase changes in carefully controlled cycles. The working fluid is not necessarily water, but the principle that evaporation can produce cooling is central. By manipulating pressure, engineers can control when a fluid evaporates and when it condenses. Inside a refrigerator, a refrigerant travels through regions of different pressure. Lower pressure allows it to evaporate at a low temperature, absorbing heat from inside the refrigerator. Later, the refrigerant is compressed and moved through another part of the system where it releases heat as it condenses. The details are carefully engineered, but pressure is doing the same general job we have been discussing. It changes the temperature at which phase transitions occur. Your household refrigerator therefore has a distant conceptual connection to water freezing while it boils in a vacuum chamber. Both depend on the fact that phase changes cannot be understood from temperature alone. Another everyday example is aerosol spray. When a pressurized substance is released from a container, the changing pressure and rapid expansion can make the container or escaping material feel cold. Several thermodynamic effects may contribute depending on the contents, but the general experience reminds us that pressure, expansion, evaporation, and temperature are closely linked. The atmosphere provides even larger demonstrations. Rising air experiences lower pressure. As air expands under reduced pressure, its temperature can fall. Water vapor may then condense into droplets, helping clouds form. Descending air can be compressed and warm. Weather is far more complicated than a single pressure relationship, but changes in pressure and temperature are constantly interacting throughout the atmosphere. Pressure also changes with depth underwater, only in the opposite direction from climbing a mountain. Go deeper into the ocean, and the weight of the water above increases the pressure. At great depths, water experiences pressures far beyond those at the surface. If you tried to create an ordinary boiling bubble down there, it would face enormous resistance from the surrounding water. Hydrothermal vents on the deep ocean floor provide a remarkable example. Water can be heated to temperatures well above the boiling temperature familiar at the surface, and still remain liquid because the surrounding pressure is so high. Near the surface, water at the same temperature would rapidly boil. Deep underwater, pressure changes what states are possible. This is why saying that a particular temperature is hot enough to boil water is incomplete without specifying the pressure. On the ocean floor, extremely hot water can remain liquid. In a vacuum chamber, comparatively cool water can boil. The temperature scale has not failed. We simply need the second piece of information. Pressure cookers use the same idea in a much gentler range. Deep sea vents show it under enormous natural pressure. Vacuum chambers show the opposite limit. Together they reveal that the familiar boiling point is only one location among many possible combinations. Freezing boundaries also move with pressure, though for ordinary ice the changes require more careful attention. Because liquid water and ordinary ice have similar densities compared with the enormous difference between liquid and vapor, modest pressure changes have a much stronger everyday effect on boiling than on freezing. This is why altitude noticeably changes cooking temperatures, while it does not transform winter weather into something unrecognizable. The gas phase is extremely sensitive to pressure because gas occupies so much more volume. Compressing or expanding a gas changes the environment dramatically. Solid and liquid phases are much less compressible, so their boundary usually moves less dramatically with ordinary pressure changes. That difference explains why the boiling side of our story feels so spectacular. Remove enough air and water starts bubbling at temperatures where nobody expects boiling. The freezing side is quieter. It appears because the boiling drains energy from the remaining liquid, not because lowering pressure alone suddenly turns room temperature water into ice. There is also a limit to how far we can lower pressure while expecting stable liquid water. As we saw around the triple point, below a certain pressure, there is no stable region for ordinary liquid water. Ice and vapor become the relevant equilibrium phases. If ice is warmed under sufficiently low pressure, it can pass directly into vapor rather than melting into liquid first. This direct solid to gas transition is called sublimation. It is familiar from dry ice, but ordinary water ice can do it too. Snow can gradually disappear on a cold, dry day, even when the temperature remains below the ordinary melting point. Ice cubes left in a freezer for a long time can shrink. Molecules leave the ice and enter the surrounding air without producing a lasting pool of liquid water. The reverse transition can occur when water vapor turns directly into solid ice. Frost is a familiar example. Under appropriate conditions, water vapor from the air becomes ice on a cold surface, without first collecting there as ordinary liquid water. Pressure and temperature determine which of these routes is most favourable. Liquid to vapor, vapor to liquid, solid to liquid, liquid to solid, solid directly to vapor, or vapor directly to solid are all possibilities within the same substance. The path depends on where the water begins and how the conditions change. This gives us a better way to think about phases of matter. Instead of imagining solid, liquid, and gas as fixed stages arranged along a single temperature line, imagine a landscape. Temperature moves you in one direction across the landscape. Pressure moves you in another. Different regions correspond to different stable states. Moving across a boundary changes which state is favoured. An ordinary kettle takes one particular path through that landscape. Pressure stays roughly constant while temperature rises until the liquid-vapour boundary is crossed. A freezer takes another path. Pressure remains roughly constant while temperature falls across the liquid-solid boundary. A vacuum chamber follows a different direction. Temperature may begin almost unchanged while pressure drops rapidly, pushing the water toward the liquid-vapour boundary without the need for heating. Once evaporation begins, the temperature itself starts changing because energy is leaving. The path now curves through the landscape rather than moving in one simple direction. Eventually it can approach conditions where solid, liquid, and vapour appear together. This picture also helps explain why there is nothing paradoxical about boiling and freezing at once. The water is not being asked to be both extremely hot and extremely cold. Those are everyday interpretations attached to familiar pressure conditions. At low pressure, boiling can occur at low temperature. Once that is understood, the contradiction disappears. You could almost say that pressure exposes how much hidden context sits inside ordinary language. We say water is boiling and silently assume ordinary atmospheric pressure. We say water is frozen and imagine the conditions inside a household freezer. We say steam is hot, even though invisible water vapour can exist in the air around you at comfortable room temperature. Daily language is designed for daily situations, not for describing every possible thermodynamic environment. Scientists therefore try to state the conditions more carefully. A measurement of temperature becomes more meaningful when pressure is known. A phase transition is described in relation to both. If the material contains dissolved substances, composition matters as well. This becomes especially important outside Earth. Imagine landing on another planet and finding a surface temperature that seems suitable for liquid water. It would be tempting to conclude that water could form lakes there. But if the atmospheric pressure is too low, stable liquid water may not last. It could begin boiling or evaporating rapidly, cooling itself, and potentially freezing. If pressure is extremely high, the phase behaviour changes in another direction. Planetary scientists therefore study combinations of pressure and temperature rather than temperature alone. The question is not simply whether a planet is warm enough for water, it is whether the environmental conditions allow water to remain liquid for meaningful periods. On Earth, we happen to live in a pressure range that gives liquid water a wonderfully broad role at the surface. Oceans can remain liquid, rain can fall, rivers can flow, ice can melt into water rather than jumping directly into vapour. These facts feel inevitable because our planet has always been our reference point, but from a broader physical perspective they depend on a fortunate combination of atmospheric pressure and temperature. That combination has also shaped life. Organisms evolved in an environment where liquid water is readily available. Our cells rely on it. Our chemistry depends on it. The atmosphere above us, therefore, does more than give us air to breathe. Its pressure helps create the conditions under which the liquid medium of life remains stable across much of the planet. Take that pressure away and water becomes far less cooperative. Inside a vacuum chamber, the transformation happens quickly enough to watch. As air disappears, the familiar rules shift. The water begins bubbling. Energy leaves with the vapour. The remaining liquid cools. Ice appears. What first looked like a contradiction becomes a demonstration of just how strongly pressure controls phase behaviour. And once pressure has shown us that boiling does not necessarily mean hot, and freezing does not exist as an isolated temperature rule, the next question becomes more microscopic. Pressure and temperature describe the overall conditions, but water itself is made from molecules, and those molecules are the ones actually moving, colliding, separating, arranging themselves into ice, and escaping into vapour. To see why all these pressure changes have the effects they do, we need to move away from the container and look much more closely at what the water molecules themselves are doing. When we look at a glass of water, almost everything that matters is happening at a scale we cannot see. The surface may appear still, the glass may feel cool in your hand, and the water may seem like one continuous substance with no particular activity inside it, but at the molecular level, the scene is crowded and restless. Water molecules are moving constantly. They rotate, collide, change direction, pull on nearby molecules, break away from temporary neighbours, and form new arrangements almost immediately. Even when the water looks completely calm, there is no true stillness inside it. That motion is what connects temperature, pressure, boiling, freezing, and the strange possibility of seeing water move toward vapour and ice at nearly the same time. A water molecule is small enough that our ordinary ideas about objects become difficult to apply. You cannot imagine it as a tiny droplet of water, because a droplet already contains an enormous collection of molecules. A single molecule is made from oxygen and hydrogen atoms joined together in a particular arrangement, and that arrangement gives the molecule an uneven distribution of electrical charge. One region of the molecule behaves slightly more negatively, while other regions behave slightly more positively. Because of this, neighbouring water molecules attract one another. They do not lock together permanently in liquid water, but they form temporary connections that are constantly appearing and disappearing. These attractions are one of the reasons water behaves differently from many simple liquids. The molecules do not simply bounce around without caring about their neighbours. They are always influencing one another. A molecule may be pulled toward one nearby molecule while another approaches from a different direction. A temporary network forms, breaks, and rearranges. The entire liquid is therefore full of structure, but it is structure that changes incredibly quickly. Temperature affects how energetic this motion is. When water is warmer, the molecules move more vigorously on average. They collide more strongly, rotate more rapidly, and are more capable of escaping the attractions of their neighbours. When water is cooler, the average molecular motion decreases. The molecules still move, even in very cold water, but they have less energy available for breaking away from one another. This does not mean every molecule in a warm sample is moving at exactly the same speed. That would make water much simpler than it really is. At any moment, some molecules have more energy than average, and some have less. Collisions continually redistribute energy among them. One molecule may gain energy during a collision, and another may lose some. The population contains a range of molecular motions. That range explains evaporation. Imagine the surface of a glass of water. Molecules near the surface are attracted to other water molecules around and below them, but unlike molecules deep inside the liquid, they do not have water molecules surrounding them equally in every direction. Occasionally, one of the more energetic molecules near the surface has enough motion to escape the attractions, pulling it back toward the liquid. It leaves the surface and enters the air as water vapour. This can happen at temperatures far below boiling. A wet towel dries, a puddle disappears. Water left in an open glass slowly becomes less abundant. None of this requires the water to boil because evaporation happens at the surface and depends mainly on some molecules having enough energy to escape. The molecules that escape tend to carry more energy than the average molecule left behind. That is why evaporation causes cooling. Remove some of the more energetic molecules from a collection, and the average energy of what remains decreases. The effect is familiar on your skin. Water evaporating from your body removes energy and leaves you feeling cooler. Boiling takes the same basic transition from liquid to vapour and allows it to happen throughout the liquid instead of mainly at the surface. To understand why pressure matters so much, imagine a tiny pocket of vapour trying to form between water molecules below the surface. For that pocket to become a visible bubble, it has to push surrounding liquid out of the way and survive the pressure acting on it. If the surrounding pressure is high compared with the tendency of water molecules to enter the vapour state, that small pocket does not last. The surrounding liquid pushes inward and the bubble collapses. Increase the temperature and more molecules have enough energy to maintain vapour inside the bubble. Lower the outside pressure and the bubble has less force working against it. Either change can make boiling easier. This is why lowering pressure can make cool water boil. The molecules have not suddenly become extremely energetic. The obstacle they must overcome has become smaller. Inside a vacuum chamber, this change can happen quickly. Air is removed, which means fewer gas molecules remain above the water to press on its surface. As the pressure falls, vapor bubbles that would have collapsed under ordinary atmospheric conditions can survive. Water molecules enter those bubbles, the bubbles grow, and boiling becomes visible. At first glance, this looks like heating because our eyes have been trained to associate bubbles with hot water. At the molecular level, however, the situation is almost the reverse. Molecules are escaping from the liquid in large numbers, and those escaping molecules are carrying energy away. Every molecule that moves from liquid into vapor must separate from the attractions of its neighbors. That requires energy. When there is no heater replacing the energy being lost, the liquid supplies it from its own internal energy. The remaining water becomes colder. This is the molecular reason boiling can eventually lead to freezing in a low-pressure environment. As the water boils, higher energy molecules continue escaping. Collisions inside the remaining liquid redistribute what energy is left, but the overall average keeps falling. Molecular motion becomes less vigorous. The constantly changing network of attractions among the water molecules becomes increasingly able to organize into the structure associated with ice. Freezing is not simply molecules stopping. Even in solid ice, molecules still have motion. They vibrate around positions within the crystal structure. What changes is that they no longer move freely past one another in the way they do in a liquid. The molecular arrangement becomes much more organized. Ordinary ice has a particularly open structure. Water molecules arrange themselves so that their attractions can fit together in a repeating network. The arrangement leaves more empty space than exists in liquid water, which is why ice is less dense and floats. For liquid water to freeze, molecules must begin forming a stable piece of this ordered structure. That first formation can be surprisingly difficult, because a tiny cluster of ice molecules may not be stable enough to survive. Molecules around it are still moving and colliding, and the small ordered region can break apart before it grows. This beginning of a new solid structure is often called nucleation. The word sounds technical, but the idea is straightforward. Freezing needs somewhere to start. A small imperfection in a container, a dust particle, or some other surface can help water molecules arrange themselves into the first stable pattern of ice. Once a sufficiently stable piece forms, nearby molecules can join it and the solid grows. This is why very pure water can sometimes remain liquid below the temperature where we usually expect freezing. If there is no convenient place for an ice crystal to begin, the liquid can become supercooled. The molecules have low enough energy for ice to be favourable, but the transition has not yet found a stable starting point. Disturb such water, or introduce a suitable surface, and freezing can spread very rapidly. The sudden transformation looks almost magical, but again the molecules are simply finding a route into a more stable arrangement. In the boiling and freezing experiment, the situation is more complicated because several molecular processes are happening together. Some molecules are leaving the liquid and entering vapor. That removes energy. Other molecules are losing enough energy to join the growing ice structure. Vapor molecules may also collide with liquid or solid surfaces and return. Nothing requires every molecule to follow the same path. This is the part that matters most when we say water can boil and freeze at the same time. The same individual molecule is not boiling and freezing simultaneously. One molecule may leave the liquid and enter the vapor. Another may become incorporated into ice. Others remain liquid. The sample as a whole supports more than one phase transition at once. Our everyday language sometimes makes phases sound like decisions made by the entire container. We say the water freezes as though every molecule receives the news together. We say the water boils as though the liquid becomes one coordinated machine. Real phase changes happen locally and statistically. Different molecules do different things, and the visible state of the substance emerges from the combined behavior of an enormous population. That becomes easier to understand if you imagine standing beside a very busy station. Some people are entering through one door, others are leaving through another, some are waiting inside, and others are transferring between platforms. If you only looked at the total number of people, you might miss all that movement. A phase boundary works in a similar way. Molecules cross in both directions. At the surface between liquid water and vapor, molecules leave and return. At the surface between ice and liquid, molecules melt away and others freeze onto the solid. At the boundary between ice and vapor, molecules can move directly between those phases as well. Under ordinary conditions, one direction may dominate strongly enough that we notice a clear overall change. Put an ice cube into warm water and more molecules leave the ice than join it, so the cube melts. Cool liquid water sufficiently and more molecules become part of the solid structure than leave it, so ice grows. Heat water in a kettle and eventually vapor formation becomes fast enough for boiling. Under carefully controlled conditions, the rates can become balanced. This is the molecular picture behind phase equilibrium. The amount of each phase can remain nearly constant, even while individual molecules constantly switch from one to another. At the triple point, this becomes especially interesting because solid, liquid, and vapor can all coexist. Molecules may move from ice to liquid, from liquid to vapor, from vapor back to liquid, from liquid into ice, and directly between solid and vapor. The visible amounts can remain steady if those transitions balance. Nothing about the molecules changes their chemical identity during these ordinary phase transitions. A water molecule in ice is still a water molecule. A water molecule in liquid is still the same kind of molecule. A molecule in vapor has not become a new substance. What changes is its relationship with the molecules around it. In ice, the relationships are comparatively organized and persistent. In liquid water, they are constantly rearranging. In vapor, the molecules are usually much farther apart and interact less frequently. That distinction is important because people sometimes imagine vapor as water molecules becoming larger, lighter, or somehow less substantial. They do not. The spacing changes dramatically, not the basic identity of the molecule. A container of water vapor therefore contains much more empty space between molecules than the same amount of material in liquid form. This is one reason pressure has such a strong influence on the liquid to vapor transition. Creating vapor means allowing molecules to spread into a much larger volume. High external pressure resists that expansion. Low pressure makes it easier. The solid to liquid difference is much smaller in volume, although water adds its unusual twist because ordinary ice occupies more space than the corresponding liquid. That open ice structure is a consequence of the geometry of the molecular attractions. If we could somehow watch the freezing process closely enough, we would see molecules that had been tumbling and rearranging in the liquid settle into more stable positions. They would not become motionless. They would vibrate within the structure. Lower temperature generally means those vibrations become less energetic. If we then added energy, the vibrations would increase. Eventually, the solid structure would become difficult to maintain. Molecules would leave their positions and begin moving more freely. Melting would occur. Add still more energy under suitable pressure, and more molecules could escape into vapor. But once pressure is allowed to change, the simple sequence of cold, solid, warmer liquid, hotter gas no longer tells the complete story. The surrounding pressure can shift where each transition becomes favourable. That brings us back to the vacuum chamber. Lower pressure removes much of the resistance to vapour formation. Liquid molecules can escape at a much lower temperature. Their escape cools the remaining water. As cooling continues, ice becomes favourable. The system now contains molecules following paths that we usually associate with opposite temperature directions. Some are gaining enough freedom to enter the gas phase because pressure is so low. Others are settling into the solid structure because the remaining liquid has lost energy. Seen from the molecular scale, there is no contradiction at all. This also explains why the process does not continue indefinitely in exactly the same way. As the water cools, the rate at which molecules can enter vapor changes. As ice forms, the amount of liquid available changes. Heat may flow into the container from the surrounding laboratory. Vapor may be removed by the vacuum pump. The pressure may continue falling. The entire system evolves as several processes influence one another. In a real experiment, the container matters too. A glass vessel, metal chamber, or laboratory flask can supply heat to the water if it begins warmer than the water. The surrounding room can also provide heat through the chamber walls. That incoming energy may slow freezing or support continued evaporation. Scientists therefore pay close attention to how heat enters and leaves the system. The visible bubbling is only the easiest part to notice. Much of the important physics involves invisible energy transfer. When one molecule escapes into vapor, we do not see the energy it carries. When another joins the crystal lattice of ice, we do not see the energy released into its surroundings. Yet those exchanges determine how the temperature changes and which phases grow. Freezing itself releases energy. This may sound surprising because we associate freezing with removing heat. But when liquid water molecules settle into the more ordered solid structure, energy is given up. That energy must go somewhere. For freezing to continue efficiently, the surroundings need to carry that released energy away. This is why the cooling story in the vacuum chamber is a balance rather than a simple slide toward lower and lower temperature. Vaporization removes energy strongly, while freezing releases some energy as the solid forms. Heat can also enter from the container. The actual temperature reflects the competition among these processes. Phase changes often create this kind of temperature stability because energy can be redirected into changing molecular arrangement rather than simply changing molecular motion. During ordinary boiling at steady pressure, continued heating can produce more vapor while the liquid remains near its boiling temperature. During melting, incoming energy can turn more solid into liquid, rather than immediately producing a large temperature rise. At the molecular level, energy is being used to change how strongly molecules are bound to their neighbours and how freely they can move. This also helps explain why water has a relatively large capacity to absorb energy compared with many other familiar substances. Its network of molecular attractions gives incoming energy many ways to be distributed through motion, rotation, vibration, and rearrangement. That property helps oceans moderate climate and helps living organisms resist rapid temperature changes. The same molecular attractions that make water biologically useful are also involved in the strange physics of ice and boiling. Water's unusual solid structure, strong surface behavior, relatively high boiling temperature under ordinary pressure, and many of its other familiar properties are linked to the way its molecules interact. Even surface tension comes from these molecular attractions. Molecules at the surface experience an uneven pull because there are more neighbouring water molecules beside and below them than above. The surface therefore tends to contract, which is why small droplets become rounded and why some light objects can be supported by the surface under suitable conditions. During boiling, surface tension affects the formation of bubbles. A very tiny bubble has a curved surface that makes it harder to grow. This is another reason boiling often begins at particular locations rather than appearing uniformly from nowhere. Look inside a saucepan and you may notice bubbles beginning on scratches or tiny imperfections in the metal. These locations provide useful places for vapor pockets to form. They are known as nucleation sites. Much like imperfections can help ice crystals begin growing during freezing. A perfectly smooth container with extremely pure water can therefore behave differently from an ordinary saucepan. Water can sometimes be heated above its expected boiling temperature without producing normal bubbling because suitable nucleation sites are missing. This is called superheating. If the liquid is then disturbed, rapid boiling can occur suddenly, which is one reason heating very pure water in smooth containers requires care. So both boiling and freezing can be delayed even when temperature and pressure suggest that a new phase should be favourable. Molecules may need a place to begin organising the transition. Freezing can wait for an ice nucleus. Boiling can wait for a vapour bubble that can survive. This makes the microscopic picture much richer than the simple schoolbook idea of reaching a particular temperature and instantly changing state. The molecule-by-molecule view also tells us why impurities matter. Dissolve another substance in water, and the water molecules now share the liquid with different particles. Those particles change the statistical behaviour of the liquid and can shift the conditions where freezing and boiling occur. Salt water freezes differently from pure water because dissolved ions interfere with the formation and stability of the ordinary ice structure. The liquid can remain stable at lower temperatures than pure water under similar pressure. Dissolved substances can affect boiling as well. The details depend on the material and concentration, but the general lesson is that phase behavior depends not only on temperature and pressure, but also on what molecules are actually present. For the cleanest demonstration of the relationships we've been discussing, scientists therefore prefer purified water and controlled equipment. The fewer uncontrolled ingredients in the system, the easier it becomes to interpret what the molecules are doing. Yet even with very pure water, the behavior remains a statistical process involving unimaginable numbers of molecules. No individual molecule carries information about the overall temperature of the container. Temperature emerges from the collective distribution of energy. No molecule knows the pressure reading on a gauge. Pressure emerges from countless molecular collisions with surfaces. No molecule is aware that scientists have labelled one region solid and another liquid. Phases emerge from patterns of molecular arrangement and motion. This is one of the reasons thermodynamics can feel both simple and strange. At the large scale, we use a few quantities such as temperature and pressure to describe the material. At the small scale, an enormous amount of activity produces those quantities. A pressure gauge gives one number, but that number represents countless gas molecules striking surfaces. A thermometer gives one temperature, but that temperature represents the average behavior of a vast molecular population. A piece of ice looks like one solid object, but inside it an enormous number of water molecules vibrate within organized structure. When we watch water boil and freeze under low pressure, we are seeing those large-scale descriptions intersect. Pressure has been changed enough to encourage vapor formation. Vaporization changes the energy distribution of the remaining liquid. Lower energy favors the ice structure. Several molecular pathways become active together. If you were able to choose one molecule at random during the experiment and follow it, its journey might be surprisingly complicated. It could begin in the liquid, collide with neighbors many times, approach the surface, lose energy, move away again, later gain energy from another collision, escape into a vapor bubble, travel through the chamber, strike a cold surface, and become part of liquid or ice somewhere else. Another molecule might remain in the liquid until an ice crystal grows toward it, then settle into the crystal structure. The visible experiment hides all these individual histories. What we see is bubbling water and spreading ice. What the molecules experience is a constantly changing landscape of energy, attraction, collision, spacing, and pressure. That distinction is worth remembering before we move closer to the actual laboratory setup, because the famous demonstration can look almost too simple. A container holds water, air is pumped away, the water begins boiling, and then ice appears. This sequence is easy to watch, but every visible stage is the result of molecular processes occurring far faster and in numbers far larger than our senses can follow. Once the chamber, pump, container, and timing are brought into the picture, those invisible processes become visible as a sequence we can observe directly. And the details of the setup explain why some versions of the experiment produce gentle bubbling, others produce vigorous boiling, and some allow the freezing to spread so clearly that the water seems to change its mind in front of you. Imagine the experiment beginning with almost nothing dramatic at all. A clear container holds a small amount of ordinary liquid water. The water is not steaming, there is no ice floating in it, and nothing about the setup suggests that two opposite-looking phase changes are about to appear. The container sits inside a chamber that can be sealed from the surrounding air. A vacuum pump is connected to that chamber, and once the system is closed, the pump begins removing air. If you were watching through the transparent wall, the first few moments might seem slightly disappointing. The water still looks like water. The container still looks like a container. There is no sudden transformation, and anyone expecting instant scientific fireworks might begin wondering whether the pump has remembered to come to work. But the most important change is already happening. The pressure surrounding the water is falling, and although pressure is invisible, that quiet reduction is changing the conditions under which the water can remain liquid. As air is removed from the chamber, fewer gas molecules remain above the water. Under normal conditions, the atmosphere presses against the liquid surface continuously. We rarely notice this because the same atmosphere presses against everything else around us, but the pressure is very real. Inside the chamber, the pump gradually takes that support away. The liquid does not immediately understand this in any human sense, of course, but the molecules respond to the new environment. Molecules at the surface have an easier time escaping, because there are fewer gas molecules above them and less pressure opposing the formation of vapour. Tiny vapour pockets that would normally disappear become more likely to survive. Eventually the pressure falls far enough that the water reaches the conditions for boiling at its current temperature. Then the bubbles begin. This is the moment that gives the experiment its first surprise, because the water may still be close to ordinary room temperature. Nobody has placed a flame beneath it. Nobody has switched on a heater. The water may even be getting colder, yet it is visibly boiling. Bubbles form inside the liquid, rise toward the surface, and burst into the low pressure space above. If you saw only this part of the experiment without being told anything about the vacuum chamber, you might assume the water had been heated. Our brains are extremely confident about bubbles. Bubbles in water mean hot. That connection usually serves us well, which is why kettles are useful, and why grabbing a boiling saucepan with bare hands remains a poor research method. Inside the vacuum chamber, however, boiling has been produced by changing pressure rather than by adding heat. The exact appearance of the first bubbling depends on the equipment and the water. Sometimes small bubbles appear gently. Sometimes the boiling becomes vigorous quite quickly. Some early bubbles may also come from dissolved gases leaving the water as the pressure falls. Ordinary water contains gases that entered from the surrounding air, and when the pressure above the liquid is reduced, some of those gases can come out of solution. This means not every bubble seen during the earliest part of a vacuum demonstration must be water vapour. As the pressure continues downward, however, vaporization becomes increasingly important, and genuine boiling takes over. The container itself can influence what you see. Microscopic scratches, rough surfaces, tiny particles, and other imperfections can provide places where bubbles begin forming. Creating a bubble inside perfectly uniform liquid is harder than creating one around a small existing pocket or surface irregularity. An ordinary glass or laboratory vessel therefore contains countless small features that can help the process start. This is why bubbling may first appear at certain spots, rather than everywhere at exactly the same moment. Once boiling becomes established, the next part of the experiment is already beginning even though it remains invisible. The water is losing energy. Turning liquid water into vapour requires energy because molecules must separate from the neighbours that attract them. The molecules leaving the liquid carry energy away. In a kettle, this loss is not obvious because the heating element or flame keeps supplying more energy. The water can boil continuously, while the heater replaces much of what is carried away by the escaping vapour. In the vacuum chamber, there may be no heater at all. The energy required for vaporization must come largely from the water and its immediate surroundings. The result is cooling. This creates the unusual situation where vigorous boiling does not indicate rising temperature. The boiling is helping the temperature fall. Molecules escape, energy leaves with them, and the remaining liquid becomes colder. More molecules escape, more energy leaves, and the cooling continues. The process is closely related to the cooling you feel when water evaporates from your skin, except that the low pressure in the chamber can make the vaporization much more intense. If a temperature sensor were placed carefully in the water, its reading would begin moving downward. The liquid that looked as though it had been heated would reveal itself to be cooling. This is one of the most satisfying moments in the demonstration because it forces us to separate appearance from physical meaning. Bubbles tell us a liquid is boiling. They do not tell us why it is boiling, and they do not tell us whether its temperature is increasing or decreasing. The water can cool surprisingly quickly because vaporization carries away a substantial amount of energy. The chamber walls and the container may supply some replacement heat from the surrounding room, but if the evaporation is fast enough, energy can leave the water faster than it arrives from outside. The liquid temperature therefore continues dropping. As it approaches the ordinary freezing region, the character of the experiment begins to change. The boiling may still be visible, but the water is no longer merely a cool liquid producing vapor. Conditions are becoming favourable for solid ice. Freezing still needs somewhere to begin. Water molecules must organise into the crystal structure of ice, and forming the first stable piece of that structure can sometimes be difficult. A container surface, a small impurity, or an existing microscopic structure can help. In some demonstrations, the water may cool slightly below the temperature where ice would normally be expected before visible freezing begins. Then, once a stable ice crystal forms, growth can proceed more quickly. The first ice may appear as a small cloudy patch, a thin layer, or a cluster spreading from part of the container. The exact shape varies with the setup. The water may become slushy rather than turning immediately into one solid block. Bubbles can continue appearing through or around the forming ice. The result is the image that makes the experiment memorable. Liquid water is visibly producing vapor, while solid water is appearing in the same container. It looks as though someone has placed a kettle inside a freezer and persuaded both appliances to win at the same time. The reality is more orderly. The boiling is happening because pressure is low. The freezing is happening because the boiling has removed enough energy to cool the remaining water. The two processes are connected rather than competing. This is important because a casual description can make the experiment sound as though water somehow reaches a temperature that is both extremely hot and extremely cold. It does not. The water is cold. It can boil while cold because the external pressure has been reduced enough. Once this is understood, the apparent contradiction disappears. The experiment also reveals something about the meaning of temperature during a phase change. When ice begins forming, energy is released as molecules join the solid structure. Freezing therefore partially opposes the cooling caused by vaporization. Some of the energy removed through evaporation is effectively balanced by energy released as liquid becomes solid. At the same time, heat can leak into the system through the container walls. The final behaviour depends on the competition among all of these energy transfers. This is why the water does not necessarily continue cooling at the same rate throughout the experiment. The process is dynamic. Vaporization removes energy. Freezing releases energy. The chamber walls supply heat. The pump removes vapour and helps maintain low pressure. Each part affects the others. The pump is especially important because vapour produced by the water increases the amount of gas inside the chamber. If that vapour were allowed to accumulate indefinitely, the pressure would rise and vigorous boiling would slow. By continuing to remove gas, the pump helps maintain conditions where water molecules can keep escaping. Different vacuum pumps and chamber designs therefore produce different-looking demonstrations. A powerful pump may lower pressure rapidly and remove vapour efficiently, producing intense boiling and strong cooling. A weaker system may show slower changes. The amount of water also matters. A small sample has less total energy stored within it and may cool differently from a large volume. The shape of the container changes how easily heat flows in from the surroundings and how much surface area is available for evaporation. Even the starting temperature changes the sequence. Begin with warmer water and more energy must be removed before freezing can start, although vaporization may initially be stronger. Begin with cooler water, and the path toward ice may be shorter. The basic physics remains the same, but the visible timing can vary. This is worth mentioning because demonstrations sometimes create the impression that there is one exact script the water must follow. Real laboratory systems are messier. Some versions show spectacular bubbling followed by obvious freezing. Others show a more gradual transition. In some, a large fraction of the water may evaporate before much ice becomes visible. In others, heat transfer through the container may prevent freezing unless the vacuum is maintained effectively. The purity of the water matters as well. Dissolved salts and other substances alter freezing behavior. Dissolved gases can affect the first stage of bubbling. Very pure water can sometimes behave differently because there are fewer convenient places for bubbles or ice crystals to begin. This is why careful scientific demonstrations pay attention not just to water, but to what kind of water is being used. Suppose the experiment is arranged well and the process continues. A growing portion of the sample may become ice while vapour continues leaving the chamber. If pressure remains below the conditions where liquid water is stable, the behaviour can shift again. Ice itself can lose molecules directly into vapour without first melting into a persistent liquid. This direct transition from solid water to water vapour is sublimation. We normally associate it more strongly with dry ice, but ordinary water ice can sublime too. Ice cubes slowly shrinking in a freezer provide an everyday example. Snow can disappear during cold, dry weather without producing the amount of liquid water you might expect from melting alone. Inside the vacuum chamber, sublimation can become much more noticeable because the pressure is low and vapour is being removed. Once much of the liquid has frozen, the remaining ice can continue losing molecules into the gas phase. That process requires energy as well, so the solid can remain cold while gradually disappearing. The experiment therefore has several possible stages. Liquid begins boiling because pressure falls. Boiling cools the liquid. Ice forms. Then, under continued low pressure, some ice can pass directly into vapour. This sequence is closely related to the principle used in freeze-drying. Freeze-drying begins by freezing material that contains water. The surrounding pressure is then reduced so that the ice can move directly into vapour, rather than melting back into liquid. The vapour is removed, leaving the material dry, while often preserving much of its original structure. Foods, pharmaceuticals, biological samples, and other materials can be processed this way. A strawberry that has been freeze-dried and a flask of water boiling into ice therefore belong to the same broad family of phase behaviour. One may be sold as a snack, and the other used to make a physics demonstration, which is perhaps more overlap between laboratory thermodynamics and breakfast than anyone requested. Freeze-drying works well because avoiding a normal liquid stage can help preserve delicate structures. If frozen water inside a material simply melted, the liquid could move around, dissolve components, collapse pores, and change the shape of the material. Removing the water as vapour directly from ice can reduce some of that disruption. The vacuum boiling experiment lets us watch the first part of this thermodynamic journey in a very clear way. Instead of beginning with already frozen material, we begin with liquid water and use evaporation itself to provide enough cooling for freezing. There is a lovely efficiency to this. The same process that removes water also cools what remains. You can see related ideas in many evaporative cooling systems. In hot, dry climates, water evaporation can be used to cool air. Traditional porous clay containers can keep water cooler because a small amount seeps through the material and evaporates from the outer surface, carrying energy away. Sweat cools the human body in the same fashion. The vacuum chamber simply creates conditions where evaporation becomes extremely easy. The role of the chamber is to let us exaggerate an effect that is already around us all the time. A puddle cooling slightly as it evaporates is easy to overlook. A container of water boiling until ice forms is much harder to ignore. If you could watch the experiment both from outside and at the molecular scale, the two views would tell very different stories. From outside you would see bubbles, movement, perhaps mist or vapour, then patches of ice. At the molecular level, some water molecules would be escaping from the liquid, others colliding with surfaces, others losing energy, and still others settling into the ordered arrangement of the growing solid. The molecules that escape into vapour do not all disappear immediately from the chamber. Some travel until they strike a wall, some return to the liquid, some may encounter a colder surface and condense or freeze there. The pump removes many from the chamber, which helps keep the vapour pressure low. The surfaces inside vacuum systems therefore become part of the experiment. In precision equipment, scientists may need to account for water molecules sticking to walls, leaving walls, condensing on cold parts, and being carried away by the pump. Anyone who thinks empty space in a vacuum chamber means literally nothing is present would discover that laboratory vacuum is more complicated. There are always molecules somewhere, and water has an annoying habit of being among them. Water vapour clings to surfaces very effectively, which is one reason creating extremely good vacuum conditions can require careful preparation. Chambers may be cleaned, dried, and sometimes warmed to drive off molecules attached to the walls. For our demonstration, the vacuum does not need to reach the most extreme levels used in advanced physics experiments, but the same general issue is present. The chamber is never simply a perfect empty box. The thermometer presents another interesting difficulty. If you want to know exactly what the water temperature is while it boils under vacuum, the measuring device itself must respond correctly under those conditions. A probe touching the liquid can conduct heat into or out of it. The container may have temperature differences from one place to another. Bubbling changes how the liquid circulates. Once ice forms, the probe may find itself touching solid in one region and liquid in another. Scientific measurement often becomes like this. The act of measuring is not completely separate from the system. The instrument has its own mass, temperature, and thermal properties. For a classroom demonstration, approximate measurements may be enough. For high-precision work, every small effect starts demanding attention. The transparent chamber also needs to withstand the pressure difference safely. Once air has been removed from inside, ordinary atmospheric pressure is still pushing against the outside surface. We casually say a vacuum pulls inward, but it is more accurate to remember that the atmosphere outside is pushing. The chamber must be strong enough to resist that force. This is one reason vacuum experiments should use equipment designed for vacuum rather than random household containers. A vessel that is not suitable can fail under the external pressure. The physics demonstration is considerably less relaxing if the container decides to become several containers without warning. Proper laboratory setups use chambers, hoses, seals, and fittings rated for the pressure conditions involved. The pump must also be appropriate for water vapour, because large amounts of vapour can affect some vacuum systems. Once all of that equipment is working, however, the visible sequence remains beautifully simple. Start with water, lower the pressure, watch bubbles form, keep pumping, watch the water cool, wait for ice to appear. The simplicity makes the experiment one of the best demonstrations of why boiling point is not a fixed idea. You can explain pressure and phase diagrams for quite a while, but seeing cold water boil is much more persuasive. Then seeing that boiling water freeze forces the lesson even further. There is another common misunderstanding that the experiment helps correct. Some people imagine that a vacuum itself is cold. Space is often described as cold. Vacuum chambers are associated with extreme experiments, and it can therefore seem natural to assume that removing air automatically cools everything inside. A vacuum is not simply a substance with a cold temperature waiting to chill objects. The water cools mainly because it is evaporating and losing energy. If you placed an object in a vacuum without a comparable cooling mechanism, its temperature would depend on how it exchanged energy with its surroundings, especially through radiation and contact with any supports. The pump does not reach into the water and pull heat out directly. It lowers the pressure, allowing rapid vaporization, and the phase change does the cooling. That distinction matters because it keeps the chain of cause and effect clear. Low pressure permits boiling. Boiling removes energy. Energy loss cools the remaining liquid. Cooling allows freezing. If you changed one part of that chain, the result would change. Suppose heat was supplied continuously to the water strongly enough to replace the energy lost through vaporization. The water might keep boiling without freezing. Suppose the pump could not maintain sufficiently low pressure. Vapor would accumulate, boiling would slow, and the cooling might not be enough to create ice. Suppose the container transferred room heat into the water very rapidly. Again, freezing might be delayed or prevented. The famous result therefore depends on producing the right imbalance. Energy must leave through vaporization faster than the surroundings replace it. When ice begins forming, another balancing act appears because freezing releases energy. The formation of the solid structure gives some energy back into the system. For more water to freeze, that energy must continue being removed. Ongoing vaporization can help carry it away. This is why boiling and freezing can support one another for a period. Vaporization promotes cooling. Cooling promotes freezing. Freezing releases some energy. Continued vaporization removes energy again. The system does not settle instantly because material and energy are constantly being redistributed. Eventually, conditions change enough that one process may become dominant. Perhaps most of the liquid freezes. Perhaps much of the water leaves as vapor. Perhaps heat entering from the surroundings establishes a new balance. The final outcome depends on how long the experiment runs and how the equipment is controlled. If the pump is stopped and ordinary air is allowed back into the chamber, the pressure rises dramatically. The conditions that permitted low-temperature boiling disappear. Bubbling stops. The ice and remaining liquid then respond to the temperature of their surroundings in more familiar ways. A container that moments earlier looked as though it had forgotten the rules of water becomes ordinary again simply because atmospheric pressure has returned. This reversibility is important. Nothing permanent happened to the water molecules. They were not chemically altered. No new material was created. The same water molecules moved among liquid, vapor, and solid states as environmental conditions changed. Phase transitions can appear dramatic while leaving molecular identity untouched. That is why this experiment is such a clean demonstration of thermodynamics. The substance itself stays chemically the same. We manipulate pressure and energy, and the physical state responds. It also gives us a way to think more carefully about what we mean when we say something has caused something else. Did the vacuum freeze the water? Not directly. Did boiling freeze it? In an important sense, yes, because the energy removed through rapid vaporization produced the cooling. Did low pressure cause the boiling? Yes. Did the water freeze because it became cold enough under those conditions? Also, yes. Several statements can describe different links in the same chain. Physics becomes clearer when we resist the temptation to compress that chain into one magical step. No mysterious cold enters the chamber. No strange kind of boiling creates ice by itself. The pump changes pressure. Pressure changes phase behavior. Vaporization transfers energy. Temperature falls, and the solid phase begins to grow. Once you have watched that sequence in your mind, it becomes possible to recognize the same principles in less dramatic places. Sweat evaporating from skin, water disappearing from a wet cloth, food drying under vacuum, refrigerants moving through cooling systems, ice sublimating in a freezer, and even water behaving on worlds with thin atmospheres all belong to the same broader story. The chamber simply lets us arrange the conditions so clearly that the relationships become visible one after another. And that raises a useful question about where else nature performs similar experiments without glass chambers, pumps, or laboratory benches, because low pressure, evaporation, freezing, sublimation, and unusual phase changes do not belong only to carefully controlled demonstrations. They also appear in technologies we use, environments on Earth, and places beyond our planet where water is exposed to conditions very different from the comfortable atmospheric pressure that normally keeps it behaving the way we expect. The strange behavior we have been following does not belong only to vacuum chambers and carefully prepared demonstrations. Once you know what to look for, the same basic physics begins appearing in places that seem completely unrelated. From a packet of freeze-dried food to snow disappearing on a cold day, from refrigeration equipment to high mountains, and eventually to worlds where the atmosphere is so thin that liquid water has trouble behaving the way it does on Earth. The laboratory experiment is useful because it isolates the effect and makes it easy to watch. but nature has been changing the rules of water through pressure and evaporation for a very long time. We simply do not always notice because outside the laboratory, several processes usually happen at once, and nature rarely provides a helpful glass chamber with a label explaining what it is doing. One of the clearest practical examples is freeze drying, a process that sounds as though someone could not decide whether to freeze something or dry it, and eventually chose both. The name is actually a fairly accurate description. Material containing water is first frozen, turning much of its liquid water into ice. The pressure around it is then reduced so that the ice can leave the material mainly by changing directly into water vapour, rather than first melting into liquid. The vapour is removed, and the material becomes dry while much of its internal structure remains intact. The process relies on the same phase behaviour we encountered when discussing the triple point. Under sufficiently low pressure, ordinary liquid water is not the stable middle step between ice and vapour. Ice can move directly toward the gas phase. This is particularly useful for foods because normal drying can change texture dramatically. Imagine a strawberry full of water. If you simply heat it strongly, the liquid water inside can move, boil, collapse delicate structures, and leave behind something quite different from the original fruit. Freeze the strawberry first and then remove much of the water as vapour under low pressure, and the solid framework can remain more open. The result is light, dry, and often surprisingly crisp. Add water again, and some freeze-dried foods can recover much of their previous character, although anyone who has eaten a freeze-dried strawberry dry will know that it also makes a perfectly respectable object in its new crunchy form. The same technique matters far beyond snacks. Pharmaceuticals, biological materials, laboratory samples, and other temperature-sensitive products can be preserved by removing water under controlled low-pressure conditions. Water supports many chemical reactions and biological processes, so reducing the amount of available water can slow degradation. Freezing the material first can also help protect structures that would be damaged by aggressive heating. The details differ greatly depending on what is being preserved, but the underlying phase physics remains familiar. Control pressure, control temperature, and water can be guided along a route from solid toward vapour without spending much time as an ordinary liquid. Long before freeze-drying machines existed, people were already taking advantage of combinations of cold, dry air and low pressure without describing the process in thermodynamic language. In high mountain environments, food can sometimes lose moisture under conditions where water spends considerable time frozen. Cold air can be very dry, and higher elevations provide lower atmospheric pressure. Ice exposed to those conditions can gradually lose molecules directly to the air. The process may be slow compared with a modern vacuum system, but it follows the same general principle. Nature does not require stainless steel equipment before allowing sublimation. Snow provides an even more familiar version. After a cold spell, you may notice that a patch of snow becomes smaller, even though the temperature has remained too low for obvious melting. Some snow can compact, some may be moved by wind, and sunlight can affect the surface, but sublimation can also remove water directly from the ice. Molecules leave the solid surface and enter the air as vapour. You do not necessarily see a puddle because the route through liquid water is not required for every molecule. The same thing happens slowly inside a freezer. Leave ice cubes for a long time and they often become smaller, rougher or oddly shaped. The freezer has not secretly been eating them, despite the evidence. Water molecules can leave the ice and enter the air inside the freezer. Elsewhere, that vapour can settle onto colder surfaces and form frost. This is why old freezers sometimes acquire thick deposits of ice in places where nobody remembers spilling any water. Moisture is continually moving through the air, changing state, and finding surfaces where it can settle. Freezer burn on food is related to this movement of water. Frozen food can lose moisture from exposed regions as ice sublimes. The vapour may migrate elsewhere in the packaging and freeze again, leaving parts of the food dry and damaged. The food remains frozen throughout much of the process, yet water is still moving. Freezing does not lock every molecule permanently into place. The molecular traffic continues, only much more slowly than in liquid water. Evaporative cooling gives us another branch of the same story, and this one is happening on your body whenever you sweat. Your skin releases water, and some of the more energetic molecules escape into the surrounding air. They carry energy away, cooling the surface. The effect is strongest when evaporation can happen efficiently. Dry moving air helps because water vapor is carried away from the skin, allowing more liquid to evaporate. Humid air makes the process less effective because the surrounding atmosphere already contains more water vapor, so evaporation becomes harder. This is why a hot, humid day can feel much more uncomfortable than a hot, dry one at the same air temperature. Your body's cooling system is trying to use a phase transition, but the atmosphere is making that transition less effective. Sweat remains on the skin instead of evaporating quickly, leaving you warm and damp, which is an impressive combination considering the entire purpose of sweating was to prevent the first problem. Some traditional cooling methods use the same idea without electricity. A porous clay vessel filled with water can become cooler than its surroundings because a small amount of water passes through the tiny pores and evaporates from the outside surface. The escaping vapor carries energy away, cooling the remaining water. The method works particularly well in dry air, where evaporation is easier. Again, there is no mysterious cold substance entering the pot. Energy leaves because water molecules leave. Modern cooling systems use more carefully controlled versions of phase change. Refrigerators and air conditioners circulate fluids chosen because they can evaporate and condense under useful combinations of pressure and temperature. Lower the pressure in one part of the system, and the working fluid can evaporate while cold, absorbing energy from the surroundings. Compress it elsewhere and the conditions change so that it can condense and release that energy outside the space being cooled. The fluid in your refrigerator is not freezing and boiling exactly like the water in our vacuum demonstration, but the larger lesson is identical. Pressure allows engineers to control the temperature at which a phase transition occurs. Once that connection is understood, refrigeration stops looking like a machine that somehow manufactures cold. It is a machine that moves energy by making a fluid change state under different pressures. The inside of the refrigerator becomes cooler because energy is absorbed there. The back of the refrigerator becomes warm because that energy is released elsewhere, along with additional energy used by the machinery. This is why standing with the refrigerator door open cannot cool a closed kitchen overall. The machine removes energy from one region and releases more energy into another part of the same room. It may make the milk happier, while making the electricity meter considerably more active. At the other end of the pressure range, cooking equipment shows how raising pressure can change water's behaviour. A pressure cooker traps steam, allowing pressure inside the vessel to rise. Higher pressure means water can remain liquid at temperatures above the boiling temperature it would have in an open pan. The hotter water and steam can transfer energy to food more rapidly, reducing cooking time. This is the opposite direction from the vacuum chamber. Instead of lowering pressure until cool water boils, we raise pressure so hotter water does not boil as easily. High-altitude cooking brings the same relationship into everyday life through geography. Climb a mountain, and atmospheric pressure decreases because there is less air above you. Water then boils at a lower temperature. Food placed in the boiling water may cook more slowly because the water is cooler than boiling water near sea level. The bubbling can look perfectly normal, but the temperature is different. This is a useful example because nothing about the saucepan has changed. The water is the same substance, the stove works in the same general way, and the cook may be following exactly the same recipe. The missing ingredient is pressure. A recipe written at one elevation can behave differently at another because the atmosphere has quietly changed one of the physical conditions. Pressure also changes water in environments where it becomes much greater rather than smaller. Deep in the ocean, the weight of water above creates enormous pressure. Near hydrothermal vents on the seafloor, water can reach temperatures far above the boiling temperature, familiar at the surface, without immediately becoming ordinary steam. At those depths, the surrounding pressure is strong enough to keep water in a dense fluid state, under conditions that would produce violent boiling near sea level. Imagine somehow taking a sample of that extremely hot deep ocean water and bringing it rapidly toward the surface while preventing it from cooling. As the pressure decreased, its behavior would change dramatically. Water that remained fluid under deep ocean pressure could suddenly find itself far above the boiling condition appropriate to the lower pressure. The environment, not just the temperature, determines what the water is able to do. The same relationship can cause trouble in machines. Liquid flowing rapidly through pumps, turbines, pipes, and around propellers can experience local drops in pressure. If the pressure falls sufficiently, small vapor bubbles can form even when the water is nowhere near the familiar boiling temperature of a kettle. These bubbles may then travel into regions of higher pressure and collapse. The phenomenon is called cavitation, and although the bubbles can be tiny, their collapse can create intense local effects. Repeated cavitation can damage propellers, pump blades, and other surfaces. Engineers therefore spend considerable effort designing equipment to avoid pressure conditions that allow excessive vapor formation. A ship's propeller may be turning through cold seawater, yet parts of that water can briefly enter the vapor phase because motion creates regions of low pressure. This is a useful reminder that when physicists talk about boiling conditions, they're not necessarily describing a saucepan. A phase transition can occur wherever the local pressure and temperature allow it. Even the sound produced by cavitation has practical consequences. In marine systems, noise from collapsing bubbles can be undesirable, and in some contexts it can make vessels easier to detect. An effect that begins with tiny regions of water-changing phase can therefore influence engineering decisions at the scale of an entire ship. Weather gives us an even larger system where pressure, temperature, and water are constantly interacting. Air near the surface can contain invisible water vapor. When air rises through the atmosphere, surrounding pressure decreases. The rising air expands and usually cools. If it cools enough, water vapor can condense into tiny liquid droplets or form ice particles, producing clouds. A cloud therefore depends on water changing state, because pressure and temperature are changing as air moves. The exact physics of cloud formation includes particles that provide surfaces for droplets and ice to begin forming, along with complex atmospheric motion. But the basic connection is familiar. Change environmental conditions and water reorganizes. This can happen repeatedly inside one weather system. Liquid droplets may freeze. Ice crystals can grow as vapor settles onto them. Ice can fall into warmer air and melt. Liquid droplets can evaporate into drier regions. Vapor can condense again elsewhere. A single water molecule moving through a storm may change phase several times before reaching the ground, assuming it reaches the ground at all. Snowflakes are particularly good reminders that vapor and ice can interact directly. Ice crystals and clouds can grow as water vapor becomes part of the solid structure. The molecule does not always need to pass through a liquid droplet first. Under suitable conditions, vapor contributes directly to the developing crystal. The beautiful geometry of snowflakes comes from the molecular structure of ice and the changing temperature and humidity encountered as the crystal grows. The resulting shapes can be extraordinarily elaborate, although the physics begins with the same water molecule we have been following since the glass on the laboratory bench. Away from Earth, pressure becomes even more important because our familiar atmospheric conditions disappear. Mars provides one of the most interesting examples. Its surface atmosphere is far thinner than Earth's, so liquid water generally faces conditions very different from those in an ordinary terrestrial lake or river. Water ice can exist, and water vapor can move through the atmosphere, but stable liquid water at the surface is much more restricted, because low pressure makes evaporation and boiling easier. If ice on a low-pressure world receives enough energy, it may begin sublimating rather than calmly melting into a long-lasting puddle. If liquid does briefly appear under suitable local conditions, rapid evaporation can cool it. That cooling may encourage some of it to freeze while another portion escapes as vapour. The combination sounds familiar because it resembles the logic of the vacuum chamber. The important point is not that every patch of water on Mars performs the exact classroom demonstration we described. Natural planetary environments involve salts, soil, sunlight, changing temperatures, wind, and many other complications. The useful connection is that low atmospheric pressure fundamentally changes the range of conditions under which liquid water can remain stable. This is why planetary scientists cannot look only at a temperature reading and decide whether a world can support surface water. Pressure must be considered. Composition matters too. Dissolved salts can lower freezing temperatures and alter evaporation behaviour. The history of the environment matters. Whether water is buried beneath soil, trapped below ice, or exposed directly to the atmosphere makes a difference. Some icy moons introduce the opposite situation. Beneath thick layers of ice, pressure rises with depth. Water may remain liquid below the surface where conditions differ enormously from those in open space above. Internal heating can provide energy, while overlying ice creates pressure. The result can be layers of solid and liquid water existing in arrangements that would seem unusual if our only reference were a glass and an ice cube. Go deeper inside sufficiently large worlds, and pressure can become so great that water forms types of ice very different from the familiar form floating in drinks. Some high-pressure forms of ice are denser than liquid water. Their molecular structures are arranged differently because enormous pressure favours more compact configurations. This gives water a surprisingly complicated life inside planets and moons. Near a surface, it may appear as ordinary ice. At another depth, liquid may exist. Deeper still, high-pressure ice phases may become stable. The simple three-state picture we learn in school is therefore only the beginning of water's phase behaviour. Comets provide another environment where sublimation becomes obvious on a huge scale. A comet contains frozen volatile materials, including water ice. When it approaches the Sun, incoming energy warms its surface. In the extremely low pressure of space, ice does not need to melt into a lake before becoming vapour. Molecules can leave the solid directly. Escaping gas can carry dust with it, contributing to the coma and tails associated with an active comet. From a human point of view, it is a remarkable transformation. An object that has spent enormous periods in the cold outer regions of the solar system approaches the Sun and begins releasing material into space. At the molecular level, however, the phase transition follows the same basic rules as ice slowly shrinking in a freezer. The environmental conditions are simply far more extreme. Spacecraft engineers also have to think carefully about phase changes in low-pressure environments. Water released into near vacuum does not behave like water poured into a sink. Without sufficient surrounding pressure, liquid water can evaporate or boil rapidly. The evaporation cools what remains, so some portion may freeze. Eventually the ice can sublime. A small amount of water exposed to vacuum can therefore pass through several phases in a surprisingly short sequence. This matters for spacecraft systems, life support equipment, thermal management, and anything involving liquids outside a pressurized cabin. The environment beyond a spacecraft is not merely cold, empty space. It is an extremely low-pressure environment where familiar liquids lose one of the conditions that normally keeps them stable. Astronauts inside a spacecraft live within carefully maintained pressure, partly because human biology depends on liquid water functioning under suitable conditions. Our bodies contain enormous amounts of water, but that water is held within tissues, blood, cells, and other biological structures. Human exposure to very low pressure is a serious medical emergency for many reasons, and the behaviour of bodily fluids is more complicated than the simple image of a glass boiling in a chamber. Still, the underlying dependence of liquid stability on pressure is one reason maintaining cabin and suit pressure is essential. Vacuum technology on Earth faces its own water problem from the opposite perspective. Scientists trying to remove gas from a chamber often discover that water molecules cling stubbornly to internal surfaces. Even after most air has been pumped away, water that was previously adsorbed onto walls can slowly escape into the vacuum. Engineers may heat vacuum equipment to encourage those molecules to leave faster, so the pumps can remove them. So water can be the object being studied in one vacuum experiment and an unwanted guest in another. Industrial vacuum systems use reduced pressure to lower boiling temperatures for practical reasons. Some liquids or mixtures contain materials that would be damaged by high temperatures. By lowering pressure, engineers can evaporate water or other solvents without heating the material as strongly as would be required under ordinary atmospheric conditions. Vacuum evaporation is used in different forms of processing where removing water efficiently matters. The exact equipment varies, but the principle remains the same one demonstrated by room temperature water, beginning to bubble when air is pumped away. Food concentration can use pressure control for similar reasons. If a liquid food is heated too strongly, flavor compounds can change and heat-sensitive ingredients may degrade. Lower pressure allows evaporation at a lower temperature. The water leaves without requiring the same degree of heating. Suddenly, the strange little laboratory demonstration begins looking less like a curiosity and more like a basic engineering tool. There is also a natural version of pressure-driven boiling in geothermal environments. Underground water can be held under pressure by surrounding rock and the weight of water above it. It may become very hot without boiling. If that water rises toward the surface and pressure falls, some of it can rapidly turn into vapor. Geysers and geothermal systems involve more complicated interactions of underground passages, heating, pressure buildup and boiling. But the relationship between pressure and boiling point is central to their behavior. Water heated underground does not ask whether it has passed the familiar boiling temperature printed in a school book. It responds to the pressure at its actual location. As it rises and pressure changes, the boiling conditions change with it. That same logic explains why steam can appear suddenly when pressurized hot water is released. Water that was stable as a liquid at high pressure may become unstable at lower pressure and rapidly produce vapor. Engineers working with boilers and pressurized hot water therefore treat pressure changes with considerable respect. A phase transition can happen quickly when the conditions move across the relevant boundary. Even ordinary canned drinks give a gentler reminder that pressure affects gases and liquids. Open a carbonated drink and the pressure above the liquid falls. Dissolved gas becomes less stable in the liquid and escapes as bubbles. This is not water boiling, but the visual similarity is useful because it reminds us that bubbles can appear for different reasons when pressure changes. A vacuum chamber containing water may initially release dissolved air before vapor boiling dominates, which is why interpreting an experiment requires knowing what the bubbles contain. Nature is full of these overlapping processes. A bubble is not automatically proof of high temperature. Ice disappearing is not automatically proof of melting. Water vapor appearing is not automatically proof that liquid water boiled. The path between phases depends on conditions. Once you begin noticing this, familiar environments become much more interesting. The shrinking ice cube at the back of the freezer is demonstrating sublimation. Sweat drying from your skin is demonstrating evaporative cooling. A pressure cooker is demonstrating the pressure dependence of boiling. Mountain cooking demonstrates the same relationship in the opposite direction. A cloud is an enormous collection of phase changes suspended in moving air. A comet is performing sublimation across kilometers of frozen surface. Freeze-drying takes these same rules and turns them into a manufacturing process. None of these examples requires water to violate anything. What changes is the combination of pressure, temperature, available energy, and surrounding material. That may be the most important lesson outside the laboratory. We often talk about the properties of a substance as though they belong to the substance alone. Water boils, water freezes, ice melts, vapor condenses. But every one of those statements is incomplete until the environment is included. Water boils under certain conditions. Water freezes under certain conditions. Ice melts. when the surroundings make liquid more stable. Vapor condenses when conditions favour molecules returning to a denser phase. The environment is part of the rule. Earth happens to give us a particular environment that makes liquid water seem normal. Our atmospheric pressure is high enough for liquid water to remain stable across a wide range of everyday temperatures. Oceans sit in the open air without instantly boiling away. Rain reaches the ground as liquid. Rivers flow. Ice melts into puddles. We have lived inside this combination for so long that we treat it as the default setting of the universe. It is not. Move upward through the atmosphere and boiling changes. Move deep beneath the ocean and it changes in the opposite direction. Remove almost all the surrounding pressure and liquid water becomes difficult to maintain. Travel to another world and an entirely different part of water's phase behaviour may dominate. The vacuum chamber is therefore doing something rather clever. It brings a small piece of an unfamiliar environment into the laboratory. Instead of travelling to a high mountain, a thin atmosphere or open space, we remove air from a container. The water then demonstrates how different the world can look when atmospheric pressure is no longer quietly holding the usual rules in place. The boiling and freezing become memorable because they reveal that our everyday categories were conditional all along. Hot does not own boiling, cold does not own freezing, liquid does not have to sit permanently between solid and gas. The routes available to matter depend on its surroundings, and a small change in those surroundings can open a path that ordinary experience never shows us. That leaves us with one final step in the story, because the experiment has done more than explain a strange behaviour of water. It has forced us to reconsider what a boiling point actually means, what a freezing point actually means, and even what we mean when we say a substance is solid, liquid, or gas. Those labels feel absolute when we encounter them in daily life, but the triple point and the pressure map behind it reveal that they are descriptions of matter under particular conditions, which is a much broader idea than anything happening inside one container of water. By the time water reaches its triple point, something very useful has happened to our ordinary picture of temperature. We began with an idea that seemed almost too simple to question. Hot water boils, cold water freezes, and somewhere between those two conditions, water remains comfortably liquid. That picture works well enough for making tea, filling an ice tray, or deciding whether a lake is likely to be frozen in winter. But the triple point shows that temperature alone never told the entire story. A particular temperature does not command matter to adopt one particular state regardless of everything else. Pressure matters. Composition matters. The way energy enters or leaves matters. The molecular structure of the substance matters. Once those pieces are included, boiling and freezing stop looking like opposite instructions and become different possible responses to the conditions surrounding the same collection of molecules. This changes what a temperature reading actually means. A thermometer tells us something about the energetic state of matter, but it does not by itself tell us whether that matter must be solid, liquid, or gas. We usually forget this because life near the surface of Earth takes place within a fairly familiar pressure range. If you tell someone that a glass of pure water is sitting at a comfortable room temperature, they will reasonably imagine liquid water. They are relying not only on the temperature you mentioned, but also on an unstated assumption that the glass is somewhere under ordinary atmospheric pressure. Put the same water into a sufficiently low-pressure environment, and that assumption disappears. A temperature that once belonged comfortably inside the liquid region can suddenly be associated with rapid evaporation or boiling. The thermometer has not changed its mind. The surrounding conditions have. The triple point makes this dependence especially clear because it gives us one temperature at which three different states can exist together. When the pressure is exactly right, ice can remain present, liquid water can remain present, water vapor can remain present. If temperature alone decided the state, this would make no sense. One temperature should produce one answer. Instead, the state of matter emerges from a relationship between variables, and the triple point is the place where three possible answers balance. This is one reason phase diagrams are more revealing than a simple list of melting and boiling temperatures. A list can make phase changes look like steps on a staircase. Reach one temperature and the solid becomes liquid. Reach another and the liquid becomes gas. A phase diagram turns that staircase into a map. Temperature is only one direction through the map. Pressure provides another. Once you have two directions, you can approach a phase boundary in several ways. A kettle moves mainly by increasing temperature, while pressure remains close to the pressure of the surrounding atmosphere. A vacuum chamber moves mainly by reducing pressure. A pressure cooker moves toward higher pressure and higher temperature. Deep ocean water exists under pressures that would be completely unfamiliar to a saucepan. Ice in the near vacuum of space lives in yet another region. The same substance can follow different paths because there is no single universal route from solid to liquid to gas. This idea reaches far beyond water. Matter in general does not carry simple labels that remain true under every possible condition. We call iron a solid because that is how we encounter it in daily life, but heat it sufficiently and it melts. Under different conditions it can become vapor. Gases can become liquids. Liquids can solidify. Some substances have several different solid structures depending on pressure and temperature. The state we normally associate with a material is often just the state favoured by the narrow environment human beings happen to inhabit. That makes the phrase state of matter slightly more interesting than it first sounds. A state is not merely what a substance is. It is how enormous numbers of particles are arranged and behaving under particular conditions. In liquid water, molecules remain close together but continually change neighbours and positions. In ordinary ice, the same molecules settle into a much more organised structure. In water vapour, the molecules are much farther apart and move through a much larger volume. The chemical identity of the water has not changed. There are still the same basic kind of molecule. What changes is the collective arrangement. This means that when an ice cube melts, nothing inside it becomes a new chemical substance. The molecules simply reorganise. When water boils, the molecules do not transform into a lighter kind of water. They become much more widely separated. When vapour condenses, those molecules return to a dense phase and begin interacting much more strongly with their neighbours. The triple point places all three arrangements beside one another and shows that the borders between them are conditional. There is also a lesson here about equilibrium. In ordinary speech, equilibrium often sounds inactive. We imagine scales sitting perfectly level or an object that has finally stopped moving. At the triple point, equilibrium is full of motion. Molecules continue crossing between phases. Some leave the liquid and become vapour. Some vapour molecules return to the liquid. Molecules join the ice. Others leave the ice. Solid can exchange with vapour as well. The overall amounts can remain steady even though the individual molecules do not. This distinction between visible stability and microscopic activity appears throughout physics. A gas in a sealed room looks like nothing much is happening, yet its molecules are moving constantly and colliding with walls. A metal object sitting on a table looks motionless, yet the atoms within it vibrate. A glass of water appears calm, but molecules leave and return to the surface continuously. The world at human scale can look still, because enormous numbers of microscopic changes average into something stable. The triple point is a particularly clean example, because several opposing processes balance at once. If evaporation became faster than condensation for long enough, the amount of liquid would decrease. If freezing outpaced melting, the ice would grow. If sublimation outpaced the reverse process, solid water would gradually disappear into vapour. At equilibrium, none of those directions completely wins. Change the conditions slightly and the balance shifts. Raise the temperature, and certain molecular arrangements become more favourable. Lower it and others gain an advantage. Change the pressure, and the widely separated vapour phase may become easier or harder to maintain. Matter does not need to be told which direction to move. The statistical behaviour of enormous numbers of molecules produces the response automatically. This is one of those points where large-scale physics can feel almost surprisingly efficient. Nobody needs to track every molecule. Nobody needs to issue instructions. Give the system a temperature, pressure, composition, and enough time, and collective behaviour emerges from molecular interactions. That does not mean every real experiment immediately reaches perfect equilibrium. Nature can hesitate. Water can remain liquid below its usual freezing condition if ice has difficulty finding a place to begin. Liquid can become hotter than its ordinary boiling condition if vapour bubbles cannot nucleate easily. Materials can become trapped temporarily in states that are not the most stable possible state. This is why phase changes sometimes happen suddenly. A supercooled liquid may remain apparently normal until a disturbance allows ice to begin forming, after which freezing spreads rapidly. Superheated liquid can remain quiet until a bubble finally forms, then boil with alarming enthusiasm. The overall conditions matter, but the microscopic route into the new phase matters too. Our vacuum experiment contains some of this complexity. We describe the sequence simply because the main idea is clear. Pressure falls, water begins to boil, vaporization removes energy, the remaining liquid cools, and ice can form. In a real vessel, however, heat enters through the walls, dissolved gases escape, bubbles begin at particular surfaces, ice nucleates somewhere rather than everywhere at once. Vapour is removed by the pump and the temperature may differ slightly across the sample. The elegant principle is surrounded by practical details. Far from weakening the lesson, those details show why experiments are valuable. Physics is not just a collection of ideal statements about imaginary substances behaving perfectly. Scientists use controlled experiments to see how the principles survive contact with real materials, real containers, real impurities, and real instruments. The boiling and freezing demonstration survives that contact very well because its central result is so clear. Lowering pressure changes the boiling condition. Vaporization cools the remaining liquid. Enough cooling produces ice. What appeared contradictory turns into a chain of ordinary events. This is often how scientific surprises work. A phenomenon looks impossible because we have carried an assumption into the situation without noticing it. Once the assumption is identified, the mystery becomes smaller. Here, the hidden assumption was that boiling requires very hot water. That statement is not universally true. Boiling at ordinary atmospheric pressure requires water to reach the familiar high temperature associated with a kettle. Boiling itself requires the liquid and vapour conditions to line up appropriately. Reduce pressure and the necessary temperature falls. Once that is accepted, cold boiling becomes possible. Once cold boiling becomes possible, evaporative cooling can push the remaining liquid toward freezing. And once that happens, the phrase boiling and freezing at the same time no longer asks water to perform two contradictory temperature tricks. It asks different molecules in the same sample to follow different phase transitions under low pressure. There is a broader lesson here about words such as hot and cold. These are useful human descriptions, but they are comparative. A cup of water can feel warm to a cold hand and cool to a hot hand. Physics needs something more precise, so we use temperature. Yet even a precise temperature does not automatically tell us everything about the state or behaviour of the material. The same is true of words such as solid and liquid. They describe patterns of behaviour at a particular scale. A solid keeps a shape under ordinary conditions. A liquid flows and takes the shape of its container. A gas expands to fill available space. These descriptions are extremely useful, but the microscopic reality underneath them is made of particles interacting according to the same physical laws. At a phase boundary, those neat categories meet. The triple point puts three of them in the same place. That does not make the categories meaningless. It shows us what they really are. They are collective behaviours rather than permanent identities. Water is especially good at teaching this because its different phases are so familiar. You have almost certainly held ice, poured liquid water, and encountered water vapour or condensed steam. There is no need to introduce an exotic substance with a name that sounds like something stored behind 3 locked laboratory doors. The strange physics is hiding inside a material that comes out of the tap. Even water's familiar solid form contains another warning against assuming matter should behave simply. Ice floats because ordinary ice is less dense than liquid water. The molecular structure of the solid leaves more open space. That one unusual fact affects lakes, climate, freezing pipes, ecosystems, and the pressure dependence of melting. Under much higher pressures, water can form other kinds of solid structures unlike the ice in your freezer. Some of those forms are denser. The complete behavior of water therefore includes far more than the three ordinary pictures of ice, liquid, and vapor. We simplify because human life occupies one small region of the full range of possible conditions. There is nothing wrong with that simplification. It would be exhausting to explain every possible phase of water before allowing someone to order an ice to drink. Problems begin only when we forget that the simplified rule has conditions attached. Science spends a great deal of time discovering those hidden conditions. Objects fall in familiar ways until air resistance is removed, and light and heavy objects reveal a deeper relationship. Clocks seem universal until motion and gravity become extreme enough for relativity to matter. Water seems to have one obvious boiling temperature until atmospheric pressure changes. Matter often looks straightforward because everyday life explores only a narrow range of the variables available to nature. The triple point is a small doorway into the rest of that range. It also tells us something interesting about measurement. Temperature feels like one of the most basic quantities imaginable. We glance at weather reports, adjust ovens, check fevers, and choose clothing based on numbers produced by thermometers. Yet creating a reliable temperature scale required scientists to decide how measurements in different laboratories could agree. A useful measurement needs reproducibility. If one thermometer says one thing and another says something different, we need a way to determine which is correct. Stable physical reference conditions provide anchors for calibration. The triple point of water became extremely important because it can be reproduced with remarkable precision when pure water is prepared under controlled conditions. For a significant period in the history of temperature measurement, it played a central role in the definition and realization of thermodynamic temperature. Modern definitions have moved toward fundamental constants, allowing the temperature scale to be grounded in properties believed to be universal rather than tied to a particular material sample. But triple point cells remain useful in precision thermometry because they provide an exceptionally stable physical reference. There is something rather satisfying about that. The strange condition where ice, liquid water, and vapor coexist is not merely an unusual demonstration. It helped human beings agree on what a temperature measurement means. A phenomenon that sounds like a contradiction became a standard of precision. That shift from surprise to usefulness happens repeatedly in science. Magnetism once seemed mysterious before becoming essential to motors and electronics. Quantum effects sounded deeply strange and now operate inside technologies used every day. Relativity can seem like an abstract discussion about clocks moving at high speed, yet satellite navigation requires relativistic corrections. Strange behavior often stops looking like a curiosity once we understand it well enough to build around it. Phase behavior is no different. Industries deliberately manipulate pressure to control boiling. Refrigeration depends on pressure-driven evaporation and condensation. Freeze-drying uses low pressure to guide ice toward vapor. Power generation, chemical processing, food production, medicine, climate science, oceanography, and planetary science all depend on understanding how matter responds to changing conditions. The glass of water in the vacuum chamber is therefore connected to a much larger network of ideas than the demonstration first suggests. It is connected to a mountaineer trying to cook dinner at high altitude. It is connected to a pressure cooker keeping water liquid at a higher temperature. It is connected to a refrigerator moving energy through evaporation and condensation. It is connected to a snowbank slowly losing ice on a dry winter day. It is connected to a comet releasing vapor as sunlight reaches frozen material. It is connected to the question of whether liquid water can remain stable on the surface of another world. The same basic phase physics appears in all of them. This brings us back to the word reality in a rather practical sense. Physics does not tell us that our everyday experience is false. Water really does normally boil when we heat it enough in an open kettle. It really does freeze when we put it in a cold enough freezer. Ice really does melt in a warm room. Those observations are correct. What physics adds is context. The rules we experience are local versions of more general relationships. Our intuition says boiling means hot, because nearly every boil we have personally watched happened under roughly the same atmospheric pressure. Our intuition says liquid water naturally sits between ice and vapor, because Earth provides pressure conditions where that liquid region is broad and familiar. Our intuition says ice and boiling belong at opposite ends of experience because kitchens and freezers rarely share vacuum equipment. Change the environment and intuition has to be updated. That is not a weakness of human perception. It is how intuition is supposed to work. The brain learns patterns from repeated experience. If you spend your entire life seeing water boil only after being heated, expecting bubbles to mean hot water is sensible. Science becomes necessary when we want to know whether the pattern continues beyond the situations we have personally experienced. Experiments extend experience. A vacuum chamber lets us experience low pressure without climbing beyond the atmosphere. A pressure vessel lets us explore high pressure without travelling deep beneath the ocean. Precision instruments let us observe changes too small for our senses. Once those new experiences accumulate, intuition can change. Perhaps after following this experiment, seeing cool water boil would no longer feel impossible. You would immediately ask what the pressure is. Seeing ice form while bubbling continues would no longer suggest that the laws of nature had taken an evening off. You would think about evaporative cooling. That is one of the quiet pleasures of learning physics. The world does not become less strange. You simply become strange in the same direction as the world. A kettle is still a kettle, but now its boiling point contains atmospheric pressure. An ice cube is still an ice cube, but now its floating shape contains molecular structure. A drying puddle is still a drying puddle, but now you can see energy leaving with escaping molecules. A patch of frost contains a direct route from vapor into solid water. The ordinary object remains ordinary while acquiring another layer of explanation, and water is unusually generous in this regard. It appears everywhere in life, weather, geology, biology, industry, and astronomy, giving us countless opportunities to see the same physical ideas repeated under different conditions. Perhaps the most useful habit to take from all of this is simply to ask what conditions are being assumed whenever a physical rule sounds absolute. Water boils at a certain temperature. Under what pressure? Water freezes at a certain temperature. What is dissolved in it and what pressure surrounds it? Ice melts when heated. Under what conditions and into which phase? Liquid water can exist on a planet. What are the surface pressure and temperature? A substance is a solid. At what temperature and pressure? The added questions do not make physics unnecessarily complicated. They reveal the information that was there all along. The triple point makes those hidden conditions impossible to ignore because all three familiar phases are present together. The usual shortcut of linking one state to one temperature fails immediately. We are forced to think in terms of relationships instead of isolated numbers. That is why this tiny region on water's phase map tells us so much. It teaches that temperature describes energy, but does not independently dictate state. It teaches that pressure can reshape the boundaries between phases. It teaches that equilibrium can involve constant microscopic change. It teaches that matter is collective behavior built from molecules rather than a set of rigid categories. It teaches that ordinary rules often contain unspoken environmental assumptions. Most of all, it explains the original puzzle without needing anything exotic. Water can boil and freeze at the same time because boiling does not require the water to be extremely hot. Under low pressure, water can boil at low temperature. As molecules escape into vapor, they remove energy from the remaining liquid. The water cools. If enough energy leaves, ice begins to form while vaporization continues. near the special conditions where solid, liquid, and vapor can all coexist. The boundaries between those familiar states come together. The water is not violating the rules, it is revealing the rest of them, and perhaps that is why demonstrations like this remain so memorable. They take something we believe we already understand and change one quiet condition. No unusual substance is required. No journey to a distant star is necessary. We begin with water, remove enough air, and suddenly a familiar liquid shows us that the rules we learned from kettles and freezers were only one small part of a larger picture. If you have a glass of water nearby, it is probably behaving itself again. No unexpected boiling, no sudden ice appearing at the surface, and hopefully no vacuum pump humming beside the bed. The pressure around you is keeping the liquid comfortably inside the region of conditions we experience every day. Molecules are still evaporating from the surface, others are returning, and countless collisions are happening inside the glass, but from where you are sitting, everything appears calm. That calmness is real, but now it comes with context. The glass is liquid because of where it sits on a much larger map of possibilities. Move the temperature, and the state can change. Move the pressure and the boundaries move with it. Push those conditions toward one particular meeting place, and ice, water, and vapor can all share the same system. Reduce pressure in the right way, and evaporation can remove enough energy for boiling water to freeze. What looked like a contradiction becomes a reminder that nature does not organize itself around the shortcuts we use to describe it. And so, wherever you are listening from tonight, whether there is rain outside, frost on the window, a half-finished cup of tea nearby, or nothing more exciting than a glass of water on the bedside table, there is a surprising amount of physics sitting quietly around you. Water does not need to be dramatic to be complicated. Most of the time it simply stays within the conditions Earth provides, following rules so consistently that we stop noticing them. But change the pressure, and suddenly those rules become visible. If you found this journey relaxing or simply enjoyed discovering that water has been keeping more secrets than its appearance suggests, you can give the video a like and subscribe to Physics with William. It helps this quiet place reach more curious listeners, and there are still plenty of ordinary things around us waiting to become slightly less ordinary. For now, there is no need to keep track of pressures, phase boundaries, or molecules changing places. The water can look after itself. You have already followed it from liquid to vapor, from liquid to ice, through the narrow conditions where all three can meet, and back into the familiar world where a glass of water, once again, looks like the simplest thing in the room. Sleep well, and if you happen to hear a kettle boiling somewhere in the distance, you may find yourself thinking not only about how hot the water is, but about the atmosphere quietly pressing down on every bubble.